about 30%. Yeah. As we go through the notes, there's slight variations on the humidity figure, but in the cabin, 30% humidity is what we're trying to achieve. Supplying the air, it kind of depends on the aircraft type as to how we're going to get the air into the cabin. There are different methods. The one we looked at the other day with the air conditioning was taking bleed air from our high bypass engines, your jet engines, and running that into the cooling packs. As that air from the bleed air system comes from the cooling packs, it's going to be heated and treated, and then it's going to get pushed into the distribution system. That air then, via the hat racks and the baggage racks, pumped into the cabin, and then it's allowed to escape via an outflow valve. If you think about pressurizing something, if we're pressurizing the aircraft, it's a bit like blowing up a balloon. If we carry on pumping pressure into the balloon, eventually it's going to burst. Not what we want to happen on our aircraft. So what we're doing is inflating the aeroplane, we're pressurizing the aeroplane, but we're allowing the air out at a controlled rate. And by allowing it out at a controlled rate, we're going to maintain the pressure in the airframe, but we're going to keep the pressure in the airframe within the limits, so we're not going to cause any structural damage. So the aircraft, as we go through that rate of change, maintain the pressure, still pumping the air in, maintaining a pressure, but the outflow valve is letting air escape at a regulated rate, so we can maintain that pressure. So from your high bypass engines, into the distribution system, your smaller turboprop engines and some of the smaller jet engines, turbine engines without the high bypass, we need to give them a little bit of assistance. So your turbine-powered aircraft, on a lot of them, what we're going to do is draw in additional air from outside. And we do that one of two ways. Again, we can use a little turbine compressor, and that turbine compressor taking a tapping of bleed air from the engine, driving the turbine, and that in turn is causing the compressor to pull air from outside the aircraft, pull air in, and we can throw that into we can treat that air and throw it into the cabin. So it's just a method of making sure that we've got sufficient air coming in. We can either use a little what's calling a turbo compressor flow multiplier, or the other way of doing that, a simpler way, is just to use a jet pump. And we know what the jet pump is. It's essentially just a little venturi. From the engine, we'll just whack a little bit of tapping of bleed air through a venturi, and that's going to introduce a flow of air from outside. That pressure drop, bringing air in from the outside, and again we can treat that air, that extra air, and throw it on into the cabin. So that is just methods of making sure that there's sufficient air for our pressurization system in the aircraft. Air tapped from the compressor of a turbine engine. Air's quite hot, used to provide heat as well as pressurization. Tapping the engine compressor can reduce the power available to the aircraft, so compressor bleed air may be used directly, or it may be used to drive a turbo compressor, which draws in atmospheric air. Mixed with the engine compressor bleed air, to give us the comfort temperatures that we want. Alternatively, the jet flow multiplier provides cabin pressurization without the complexity of the turbo compressor, and again we know how that works. Your high bypass gas turbine aircraft, your big jet engines, we're taking engine from the compressor and running it through the ACM as we described previously. So nothing there for us to worry about. We've covered those bits. We know what's going on. Yeah. Again, these are more for the ab initio guys, but you've got your engine running. Yeah. Throwing a bit of air up into the turbine. Turbine drawing in the compressor, which again is drawing air in. Yeah, and the two lots. There'll be a mixing chamber there somewhere, and then that air is going to be passed on into the cabin. Outflow valve there, just to make sure that everything's tickety-boo. Yeah, we're not going to over-pressurize the cabin. Everybody okay with that? Yeah, the Venturi or the jet pump. Yeah, same sort of thing, just a tapping of bleed air. That's going to induce a flow of air from outside, draws air in from atmosphere, normally through a knacker intake. We looked at those the other day. Again, the airflows are going to, the mix, the hot bleed air, the cold outside air, push that into the cabin. Yeah, and again, that's going to pressurize the aeroplane. Any excess out through the outflow valve. The air cycle machine, the high bypass gas turbine engine, we've talked about that before, where we're going to get air from the engines. Yeah, and we went down through our air cycle machine. We talked about that. We've got all the warning devices, the heat exchanger, the ram air coming in, and then it's going to go up to the mixing manifold, where it's going to get passed on and distributed. And because there is sufficient air in there, that air in the cabin is going to not only give us the warmth and the comfort, it's going to give us the pressurization that we need. Happy days, yeah. So from your engine through your cooling packs, off through the distribution system, and your ductwork, yeah, behind the baggage boxes and down the centre rail and all the rest of the good stuff. Don't need to worry about the bleed air control panel. We've covered that in both pneumatics and cabin conditioning. Yeah, we know we've got the control cabin in there, our control pack in there, control panel in the flight deck. Yeah, that's where we're going to turn the system on, and we can monitor what's going on with it. We've done all that little lot. Anything else we need to say there? Yeah, the amount of air supplied for cabin pressurization requires to be controlled so that a constant mass flow passes to the cabin. That prevents pressure surges and maintains an adequate amount of air to meet normal ventilation, conditioning, pressurization requirements. Also need to ensure that the required amount of air is used, especially if the air is being supplied from the compressor of the engine. So the mass flow of air requires to be maintained at a constant to give, irregardless of any changes in the volume of air supplied, all the rest of it. So the air conditioning system provides constant supply of air for ventilation. We talked about humidity. Yeah, low density, high altitude, sent into the cabin. Control of cabin pressure and rate of change is obtained by regulating the rate at which the air escapes, which we will see in a few minutes. Additionally, yeah, we're going to have a manually operated device which is available to the flight crew, by which the pressure differential can be reduced to zero. That is commonly known as the dump valve. Yeah, what the dump valve is doing is opening the cabin up to atmosphere, so that the pressure will equalize so that the pressure in the aircraft and the pressure outside the aircraft are the same. Just be aware of the dump valve. Yeah, the dump valve is there to evacuate or equalize the pressure inside and outside. The dump valve closed before we start the aircraft, before the pressurization cycle starts, and the dump valve is normally opened just before landing to make sure that everything is equalized. The example for other occasions, if you get smoke in the cabin, we can bring the aircraft down to a safe altitude where we can then open the dump valve, and that will make sure any smoke in the cabin's cleared. When we're talking about safe altitude, normally below 10,000 feet. Once you're down below 10,000 feet, the air is breathable. We don't need to provide oxygen, and that differential is well within the limits of the aircraft. Right, bottom of page 13. Yeah, the condition in an aircraft where the pressure in the cabin is greater than the ambient is defined as positive differential pressure. Yeah, so we're taking the aircraft up to altitude. We're pumping that in. We're pressurizing the airframe. Yeah. That is known as a positive differential. Yeah, so just off the slide, we're sitting on the ground. The air inside and the air outside are at an equal pressure. Once we take the aircraft up to 35,000 feet, yeah, a lot more pressure inside than outside, so that aircraft is trying to inflate. It's trying to grow and grow. That is your positive differential. Yeah. What we don't want is for that differential to become too excessive. So if for whatever reason we had a failure in the system, if the discharge or the outflow valve wasn't operating properly, we're going to put in a safety relief valve in the system as well. Again, backup. Yeah, so your positive differential, normally controlled by the cabin pressure controller, talking to the outflow valve. It's required that duplicated devices be provided that will automatically limit the differential to the maximum value. And that is achieved by the use of a cabin safety valve. Top of page 14. Stick a highlighter through that. The typical maximum differential pressures for a jet transport aircraft, 8 to 9.5 psi. For a turboprop transport aircraft, 5.5 psi. And for a turbocharged twin-engined aircraft, 4.5 psi. Those are the maximum differential pressures that we're going to allow. Yeah. Conversely, there's always a possibility where we're going to end up in a situation with the cabin pressure less than the atmospheric pressure. Let's say that the aircraft goes into a steep dive, yeah, plummets down earthwards. We can end up with the cabin pressure being lower than the ambient pressure. Yeah, that would lead to sort of crushing of the aircraft structure, because the pressure on the inside a lot higher than the pressure on the outside, a lot higher than the pressure on the inside. So it would cause it to what they call Coke can. Yeah, so it's been crushed from the outside. Again, we don't want that happening, so we're going to stick a safety relief valve in the system, but this is going to be an inward relief valve. Yeah, the maximum negative differential pressure is limited to 0.5 psi, 0.5 psi. And again, that's on page 14. Everybody okay with that so far? Any problems there? No, bro.
Yes, sir.
Yeah. Yeah, so the altitude that the aircraft's going to be flying at, the pressure altitude, there is the altitude in the standard atmosphere corresponding to a particular pressure. For those that have done aerodynamics, hopefully everybody, the atmosphere varies. The pressure at different atmospheres varies around the world. So what all the clever people did, they came up with a standard atmosphere, and they said it's kind of averaging everything out. So they've said at a particular altitude, the pressure will be. You'll get slight variations regionally. That's why they came up with this standard atmosphere. So that in the standard atmosphere, an altitude of 8,000 feet, the pressure is 10.9 psi. To all intents and purposes, we can call it 11. Yeah. So if we fly at 8,000 feet, we've got 11 psi surrounding us. If we go up to 28,000 feet, that pressure at that altitude is 4.8 psi. Yeah. It says there, if we add that pressure to the cabin pressure differential of 6.1, we can maintain a total pressure of 10.9. So flying at 28,000 feet, we can replicate the air at 8,000 feet. Yeah. So your standard atmosphere, is just a nominated pressure for a nominated altitude. Altimeter, if we set that to your 1013.25 millibars, which is your sea level, altitude indicated is the pressure altitude. Altitude in the standard atmosphere then again corresponds to the pressure as we go up. Do I need to say anything else there? Not really. Density altitude is the altitude in the atmosphere corresponding to a particular density value. Again, we don't need to worry too much about that. The different valves that we get then, we've got our control panel. We're going to have a look at that when the crew climb into the aeroplane. Depending on the type of system they've got, they're going to set the rate of change, they're going to set the cruising altitude, and the rate of change makes sure that the cabin pressure arrives at its selected value as the aircraft arrives at its selected altitude. So the crew will set all that up. The engines are going to pump that air into the cabin, and that cabin air, the release of it is going to be regulated by the discharge valves. The discharge valves, again, it's kind of aircraft dependent, but the discharge valves and the outflow valves are the same thing. It depends on the type of aircraft, the terminology that they use. But if you see outflow valve or discharge valve, they're the same thing. They're doing the same job. The cabin safety valve is there, and we'll have an inward and an outward relief valve. Again, just to make sure that differential pressure doesn't damage the structure of the aeroplane. And our dump valve, that is going to open the cabin up to atmosphere below safe level. Ta-da! We can have pressurization systems using either pneumatic control or electronic control. Again, that's pretty much dependent on the aircraft type. They're both a bit of a chew. We'll talk through them. I'll tell you now, we've got to cover it, but you don't need worry about the internal workings of any of the valves. Yeah, they're not going to ask you questions on what does valve J do and how does it affect valve M. I'll point out the bits that are essential to us as we get to them. But yeah, typical multi-engined aircraft. Yeah, air supplied by the air conditioning packs supplied by compressor bleed air. Yeah, and if the event of one failing, then the other engine will take over. Anything else we need to worry about there? Yeah, what we're going to look at in the cabin, in addition to the basic units to control that pressure, pressure limiting, your outward relief valve and inward relief valves are provided. They safeguard the cabin in the event of a control unit failure. The captain or the crew are going to have an indication of what our differential pressure is, so they know that we're going to fly within limits. 2 discharge valves. Yeah, everything again in the system is duplicated. Duplication is good. Rate of change. Yeah, we need to set up the cabin altitude and the rate of change, and that's done by the crew. Again, we'll go through that in a couple of minutes. Rate of change just governs the speed at which the cabin altitude changes. Yeah, and we can adjust that. Normal setting around about 300 feet per minute. Yeah, cabin rate of change. Close the dump valve. Happy days. Discharge valves I'll talk about in a minute. Yeah, and they're solenoid operated. And away we go. Again, just on the notes, an example of the control panel. On the slide, that's again just showing where the various components are. The outflow valve, discharge valve in this case, is a little electrically driven door. The motor taking signals from an electronic controller. Yeah, and that electronic controller, as we look at the electronic system, I'll go through it. But the controller looking at what the pressure is in the aircraft, and it's modulating that door position to regulate the flow out of the aeroplane. Our pressure controller, pneumatic pressure controller. Again, we'll go into this in a little bit more depth, but basically what it is a little diaphragm that's top half of which is connected to the controller that we're looking at. The bottom half of the thing is open to cabin pressure. Yeah, and by adjusting the pressure in the top chamber, that's allowing the cabin pressure to push up on the diaphragm, and it's allowing that cabin pressure to escape slightly. As the cabin pressure escapes, yeah, the control pressure is increasing above the diaphragm, and that's starting to close off the cabin side of the valve. So the cabin controller, again, we'll look at in more depth in a minute, but the cabin controller is modulating, and it's regulating the amount of air that it's allowing from the cabin to discharge to atmosphere. Distribution system, we've already looked at that. Yeah, the air coming out from the engines through the cooling packs, yeah, where it's conditioned, yeah, into the mixing manifold, and then off into the distribution system to wherever it needs to be. Once it's all been circulated, yeah, that air is discharged overboard via our outflow or discharge valves. Yeah, that fresh air replacement. Yeah, £1 per minute per person, and we've got the recirculation goes on as well. Nothing else to say there. A couple of nice pictures on page 16, just showing you the controller, the glass cockpit display that you might get. Yeah, just giving you the relevant information. Pressure controller. Yeah, we talked about that. Yeah, the height of the landing airfield. Yeah, we'll look at that. We'll talk about that. We've got the automatic. Yeah, up and down, and we can also control manually as well. Right, I'm just going to flee through the notes here at this point before I come onto that diagram, just to make sure I've covered everything. Section 4, we talk about the typical components in the system: the pressure controller, the discharge valve, the cabin safety valves, and it says blowout panels. The blowout panels we looked at in the structure side of things. They are there to ensure that the pressure in the cabin remains even. Yeah, so we're not going to get any differential within the cabin. So if I had a puncture of the lower fuselage, which is a non-pressurized area, the pressurized area, the non-pressurized area, if we didn't allow that pressure to equalize, we could get damage to the aircraft structure. So the blowout panels allow that to happen. The discharge valve, it's duplicated, but the discharge valve will act as a safety valve and an inward relief valve as well. I'm going to go through this, but the discharge valve, control chamber fed with cabin air through a filtered meter and an orifice. Action of the pressure controller causes the control chamber pressure to be altered to the required degree by opening a bleed from the chamber to atmosphere. Control chamber pressure related to cabin pressure on the other side of the diaphragm causes the discharge valve to regulate the outflow, which is what I was trying to point out on that one. Yeah, your control chamber, the pressure from the control acting on top of the diaphragm. Yeah, as that pressure varies, as the pressure builds up, it opens the. There's an outlet. I've got a better picture somewhere, but there's a little outlet. So as the cabin pressure sort of decreases on top of the diaphragm, the cabin air pressure is gonna lift the diaphragm. As that diaphragm lifts, cabin air pressure is allowed to eke out to atmosphere. Drop of pressure under the diaphragm. The valve starts to close off, and the pressure controller control pressure is now acting on top of the diaphragm, and that whole process is continually modulating, so that air's escaping, but we get a nice balancing act. So that's your discharge valve. Outflow valve, discharge valve. The outflow valve is that door that we were looking at, a double door. And again, they're opening and closing. There's a controller sending a signal to the door, and they are opening, closing, modulating. And that was the slide that we saw earlier. So system looking at what's happening, sending a signal to a little motor via linkage, driving the door open or closed. We don't need to worry too much about that. Certainly don't need to worry about the gears in it. And your discharge valve that we're going to come on to. The cabin safety valve, Yeah, if the pressure becomes excessive due to failure of the pressure control equipment, increase differential pressure across the pressure relief valve, diaphragm opens an internal control valve, and that air is allowed to escape. Again, I'll show you that more in just a moment. Inward relief valve, yeah, should we get a negative pressure, then again the valve opens and allows pressure to equalize. Right, what do we want to happen? Yeah, the aircraft is going to climb to its selected cruising altitude. We said that the rate of change, the rate of climb is normally about 1,000 feet per minute. Just on this illustration, it's showing it at 800 feet per minute. Same sort of thing applies. So we're going to set a cruising altitude of 25,000 feet in the aircraft, and the external pressure is around about 5.5 psi. What we want to do is to change the cabin altitude. Yeah, so as the aircraft is climbing, we want the cabin altitude to change until it gets to a point at around about 8,000 feet, which is the comfortable cruising altitude for people. So we're going to change the rate of change for the cabin altitude to around about 300 feet per minute. And we want the cabin to arrive at its selected altitude just before the aircraft gets to his cruising altitude. So we climb up to 8,000 feet in the cabin. The aircraft gets to the top of its climb. Yeah, we're just below that maximum differential of 5.5 that we talked about. And now we're going to control that pressure at 8,000 feet right the way through the journey. As we start to descend, yeah, the aircraft's going to start descending. It's going to come down a bit quicker, but now we need to start adjusting the cabin rate of descent, the rate of change. Yeah, again, we'll maintain that around about 300 feet per minute. So now the cabin altitude as the aircraft is coming down, we're changing the cabin altitude, and again at a selected height, just before the landing height. Yeah, we want the cabin pressure and the ambient pressure to have equalized. Badoom. Yeah. Right. Chapter 2, and it goes through all the operation of the internal workings of the valves. As you will see, it talks about valve F, valve L, knob C, beam K, all the rest of it. What I'm going to do is just quickly go through it. You do not, repeat, do not need to memorize any of this lot. Yeah, just know that the pneumatic controller is going to control the rate of change of cabin pressure, and the pneumatic controller, once we've reached the selected cabin altitude, is going to maintain that cabin altitude until the aircraft altitude changes. We might need to climb a bit, we might need to start to descend, but the controller is going to look after all of that little lot. So all of that on page 21, don't worry about, I'll go through it. Yeah, and away we go. So cabin, yeah, pilot jumps in, he's got his control panel where he's going to select his rate of change. We said around about 300 feet per minute. He's going to select the cruising altitude of the aircraft. Yeah, so he's going to select the altitude that he's going to go to. And his indication is going to be the rate of change of cabin altitude, the rate of change of the aircraft, and the differential pressure that the aircraft is subject to. Yeah. The cabin altitude and the rate of climb, sorry, the cabin altitude and the differential pressure can be combined on one gauge. Yeah, the rate of change indication or the cabin climb indication, again, separate gauge. So now, yeah, what his cabin altitude is, yeah, what his differential pressure is, and so long as he's within limits, and then for his differential, he's going to have a red band warning him that he's out of limits. His rate of climb, yeah, how quickly he's going to go up. Yeah, he's going to set his rate of change. Yeah, and he's going to select his maximum cabin altitude. And away he goes. Cabin rate of climb, cabin differential, yeah, cabin differential pressure indicator, cabin pressure altitude indicator, and the maximum differential, yeah. So those are the indicators that he's gonna have. Yeah, lots of working out for him to do. Yeah, setting up where he's going to go, how high he wants to be, what rate of change he wants, how long he's cruising for, and then he needs to know what his rate of change is going to be for the descent. So the crew will set all that up before they take off. Yeah, the two types of control system we have: the pneumatic control system and the electronic control system. Outflow valves, we've seen all that, don't need to worry about that. Yeah, that is your outflow valve, little electric motor, yeah, just a couple of rods, and it's opening and closing that door, modulating the position of the door. The pneumatic controller looks something like that, and that's what they look like on the aircraft. As it says on the aircraft outflows, these things move very, very quickly, so don't be sticking your fingers in there while the aircraft's running. And again, just another version. Outflow valve, yeah, door opens, closes. Yeah, moves very, very quickly. And this is what we're going to talk about in just a moment. The control of it. As I said, don't worry too much about what each of the valves is doing. I'm just going to run through and just give us an idea of what's going on. Before I do that, though, I think that's a good time just to stop and have a cup of tea. I make that 10:15 my time, so we'll have the usual 20 minutes. Yeah, and then we'll finish off pressurization. There's not a hideous amount to it. Has anybody got any questions so far?
Yes, Jim.
Yes, Jim. Go on then.
The safety valve is a backup for both outflow valve and inward relief valve, or both?
The safety valve is for a positive differential pressure. So if the aircraft is at a higher level than outside, if the aircraft continues to pressurize and you get a failure in the normal relief system, the safety valve will allow pressure out of the cabin. The inward relief valve is for negative differential pressure. So if the ambient is higher than in the cabin, the inward relief valve will allow ambient pressure in. So we can combine the functions in one valve, but the inward safety relief and the pressure control are two different functions.
Okay.
Yeah. Anybody else? No, right. We'll have a cup of tea there then, and then we'll run through the rest of this. It's not as complicated as it looks. Trust me. Trust me. I'm a gynecologist. I'll see you in a couple of minutes. Right, we've got everybody back. Looks like it, so we'll just plod on. Before I carry on, has anybody got any questions from this morning?
Feeling so sleepy, Jim.
Sorry?
Feeling so sleepy today.
Feeling
So
sleepy?
Yeah.
All right. Was that out partying, were you?
And not partying.
Rocking it down in Tamil.
Module 11 giving so much stress.
No, it's easy.
Increasing the fatigue level.
Yeah, yeah, yeah. Now, like I say, you know, you guys seem okay. So, you know, if you put in the reading in, yeah, you put in the effort in. I say it's easy. It's easy for me to say, but no, you seem to be doing all right. You know, the questions that you've been asking have been sensible. It proves that you're reading the material. You've got an understanding of the material. So if something, you know, if one of the questions it wasn't blazingly obvious to you, you've got that level of background knowledge where you could have a really educated guess at the answer. But you know, from what I've seen so far, I don't think anybody's going to have any major problems, you know, that the work that you're putting into it, you should be okay. And hopefully now, you know, that we've, you know, we're sorting out the wheat from the chaff as we go through. We should be all right.
Hope so.
Right, the pneumatic pressure control side of things. Like I said, there's a lot of writing in the notes there, and I'll come back to that in a few minutes. There's a couple of bits we need to highlight, but essentially what we're going to do with the pneumatic system is use a controller for setting up the rate of change and the altitude that we want to fly. Yeah, the rate of change, the altitude we set up on our dial on the controller. Yeah, and that controller in the flight deck. That controller is talking to the discharge valve pneumatically. Yeah, and it's that talking to the discharge valve pneumatically that is going to control the rate of change of pressure in the cabin. What we've got is the controller, 2 chambers in it, the rate of change chamber, and the control chamber. Yeah. Control chamber got a little filter on it, and that's taking air in from the cabin, and it's also taking a tapping of air in from outside. The control chamber, yeah, when we set that up, that's trapping pressure in it. Yeah, there's a set of bellows in there called the isobaric capsule, and what's happening? We're going to set the altitude. The altitude is going to control the amount of pressure that the isobaric capsule is going to have be subject to. Above that, there's a little diaphragm, so pressure in the upper chamber, pressure in the lower chamber, acting on this wee diaphragm. The rate of change, the controller there is just opening and closing an orifice, little needle valve closing an orifice, and by adjusting that, that's regulating how much pressure we're allowing out of the rate chamber. Yeah. So we set those up, off we go flying, yeah, and we start climbing. The outside air pressure is being felt in the control chamber. The rate chamber is a bit higher pressure, and what's happening as the pressure in the rate chamber is higher, it's acting on this little valve, and it is regulating the inflow of air from outside. Because it's doing that, the air in the top chamber is being felt at the discharge valve. Pressure on the discharge valve, and in here we've got cabin pressure. Yeah. Forget about the depressurizing solenoid for the time being. I'll come on to that. But your cabin pressure being felt on the bottom of the discharge valve. That's all cabin pressure going in there. The control pressure, yeah, as it's pushing down on this little diaphragm, yeah, as cabin pressure is altering, so is the control pressure, and that control pressure is just opening a little valve. As it does, it's allowing the pressure out from above that diaphragm. The cabin pressure is then opening the discharge valve. The discharge valve is then allowing cabin pressure out, reducing that cabin pressure. So now the control pressure builds up, closes off the outflow valve, and the control pressure, if you like, is allowed to build again. So the discharge valve is continually opening and closing slightly, yeah, and in doing that, it is controlling the outflow of cabin air to atmosphere. Prior to the aircraft taking off, and when the aircraft is just about to land, what we want to do is to open up the cabin to atmosphere. So the pilot will switch on the depressurizing solenoid. That then will allow bleed air into the air from the top of the chamber to escape totally, which will allow the discharge valve to fully open, and that will bring the cabin altitude, cabin pressure to the same as ambient. So basically, it's a balancing act between the pressure in the pressure controller, and the pressure in the pressure controller is modulating the discharge valve. As it modulates the discharge valve, it is regulating the amount of air being allowed to escape from the cabin. This thing works, as you can see, the diaphragm is going to open and close this little valve. As it does, cabin air is going to be allowed to escape at a controlled rate. The cabin safety valve, if we get a failure in any of this gubbins, we don't want pressure building up too much. So the cabin safety valve, pressure relief valve, essentially is just going to open up and again allow any excess to escape. The valve's duplicated again for safety, and there is a ditching handle as well. The ditching handle is there so if we land on water, it'll allow the lower half of the valve to flood, and in allowing the lower half of the valve to flood, it's going to close the cabin off to atmosphere, to that water, and it's going to stop water coming into the cabin, the ditching valve. Not a lot else to say on that. I don't want to go too deep into it. We don't need to know what all these valves are doing. The one that we need to worry about is the isobaric capsule. And as we go through the notes, start off on page 21. Pilot's going to set the range of change. During takeoff, the discharge valves are going to be open. After takeoff, they're going to be closed, and the cabin pressure will increase relative to the ambient. Air coming into the control chamber above the diaphragm decreases in pressure as the aircraft altitude increases. Air in the rate chamber beneath the diaphragm is at a slightly higher pressure, and is prevented from escaping by the rate of change control valve. Diaphragm deflects upwards, and that allows the pressure to vary in the control chamber, and by doing that, the pressure down at the discharge valve is going to alter. Pressure transmitted to the discharge valve, is that required to position it to make the cabin climb to 8,000 feet? So the discharge valve is closed as pressure's changing, then it's going to start opening and closing to allow air to escape, but to build up sufficient pressure in the cabin. The ideal, and again, this is worth sticking a highlighter through. The ideal is when the aircraft rate of climb is adjusted to arrive at the selected flight altitude slightly after the cabin reaches the height selected on the controller. So all that's saying is I'm going to cruise at 30,000 feet. I'm going to have a rate of change of 300 feet per minute. My cabin altitude needs to reach the equivalent of the cruising altitude at the same time. Doing that, we're not getting, as it says on the notes there, we're not getting any rapid changes in pressure. It's just giving a nice smooth changeover.
Where is this line, Jim?
What line?
The one you told us to highlight.
Page 21.
Page 21.
Page 21. Well, it is on my
That's good.
notes. Yeah, is that the start of chapter 2 on your notes? Page 21.
Okay.
Yeah, and it's the second last paragraph.
Oh yeah.
Third last paragraph, sorry. Just near the bottom where it says rate of change, it's the paragraph below that.
Yes. The ideal
You
is
see
when
it?
the aircraft to arrive at sleeping blood is slightly after the aircraft. Yes, I got it. Thank you.
Okay, so we've gone up to our altitude. Again, the figure in the notes, same as I've got in the on the slide. In fact, I think the one in the notes is coloured a little bit better. Just shows you that the rate chamber, yeah, the wee diaphragm, a higher pressure under the diaphragm than there is above it. Yeah. So what we're doing is allowing air to escape very, very slowly into the control chamber. That in turn is acting on that diaphragm. As that pressure acts on that diaphragm, it's going to open and close the wee valve there, which is changing the pressure in the upper chamber, which in turn is regulating the amount of pressure that we're allowing out of the cabin. Bingo. Yeah, the graph that we looked at just shows you the way that the aircraft is climbing, and we need the cabin altitude and the cruising altitude to arrive together around about the same point. Again, just worth noting at the top of page 26, should the aircraft climb above the maximum pressure altitude set on the controller, the system will no longer hold the cabin altitude. Yeah, because you can't exceed the maximum differential, the cabin altitude will increase at the same rate as the aircraft altitude. So if you haven't got the marry up quite right, the aircraft climbing and goes above the maximum pressure altitude that's set on the controller, then the system will change the cabin altitude as aircraft altitude rises. Again, that tendency to increase the differential pressure, the valve will open and allow the control chamber pressure to be reduced, which opens the discharge valve, and again that's going to help prevent the cabin differential pressure being exceeded. Centre paragraph on page 26. Yeah. Once the cabin altitude reaches the controller setting, yeah, conditions will stabilise, everything will balance out. The discharge valves will open and close to maintain the pressure equivalent to the controller setting. That is known as isobaric control. Yeah. Isobaric control is the little capsule. Once the pressures in the pressure controller have equalized, yeah, that pressure acting on the outflow valve now is nice and steady, nothing happening. Any variations, yeah, if altitude changes, that's going to be sensed. If the cabin pressure starts to increase, that's going to get sensed. That isobaric capsule will feel that pressure, and that isobaric capsule, as it expands and contracts, is going to modulate the pressure that's being felt at the discharge valve, and the discharge valve is going to open and close. It's going to modulate to keep the cabin altitude at the right level. That is known as isobaric control. Yeah. So again, halfway down page, whatever I've just said, page 26. Yeah, stick your highlighter through isobaric control and know what isobaric control is doing. Yeah.
Can you explain once, Mr. Jim, this isobaric control?
Yeah, can you just give me 1 second? Somebody's texting me.
Okay.
Right, lovely. Yeah, it's just one of my colleagues is trying to get me to phone him, but I've just sent back teaching. So obviously I'm not the only one in crisis. Right, isobaric control. The aircraft has taken off. Yeah, the control chamber is sensing the difference in pressure that's been built up. That control chamber is setting up the rate of change. Yeah, so let's say we set up 300 feet per minute. Yeah, there's air trapped under this diaphragm, and that air that's trapped under the diaphragm is being held in place by the rate of change controller. That rate of change controller is just a small orifice. Yeah, so if we set up the rate of change controller, what we're doing is allowing the air out of the rate chamber at a controlled rate. At the same time, the upper chamber, yeah, it's sensing what the outside altitude is. It's got pressure from outside acting on a little valve. It's also looking at cabin pressure. That it looks like a knob on the top, but it isn't. It's meant to be a filter. Yeah, so air from the cabin is coming into the control chamber. The control chamber is sensing that pressure. Yeah. The lower pressure in the cabin, yeah, the higher pressure in the rate chamber is causing these bellows to expand. Yeah, and the pressure's acting on a wee diaphragm, which is regulating the static pressure that's coming into the control chamber. That control chamber is sending pressure down to a little valve in the discharge valve. That pressure in the discharge valve acting on a diaphragm. Yeah. Below the we'll call that the top chamber. We'll call this the lower chamber. Cabin pressure is acting on a diaphragm in the lower chamber. Yeah, as it does, it's pushing up on the diaphragm and it's opening the discharge valve, allowing cabin air or some of the cabin air to escape. Yeah, the pressure that's acting on the discharge valve controller again is regulating the amount of air that we're allowing out of that top chamber. Yeah, so as the pressure in the top chamber builds because the cabin pressure's keeping it in there, yeah, the valve's gonna close off. Yeah, so now the rate at which we're allowing the air to escape, acting on that wee valve, which is in turn causing the discharge valve to open and close. Yeah, it's never going to fully close because there's always going to be a little bit of pressure under it, but it's regulating the flow of air that we're allowing out. Yeah, again, sorry, through a filter. Yeah, there's going to be cabin air in the top chamber, cabin air in the bottom chamber. That control air is allowing air out of the top chamber, which in turn is allowing the cabin air to go out. So that valve is constantly modulating and regulating the flow of air we're allowing out. Once we get to our 8,000 feet cabin altitude, yeah, the control chamber has got 8,000 feet acting on it. The upper chamber's got 8,000 feet acting on it. that discharge valve is going to close. So everything is sitting there fat, dumb and happy. The isobaric capsule is there, and the isobaric capsule is looking for any pressure change in the cabin relative to the pressure outside. So it's the isobaric capsule as there's any pressure change across that diaphragm. Yeah, so you're going to have, let's say 8,000 here, 8,000 here. Yeah, you've got your atmospheric pressure being felt, your ambient. So if there's any change in ascent, descent, if there's any change there, that pressure drop is going to be felt across that wee diaphragm. As it does, the isobaric capsule is going to modulate the air. It's going to allow pressure to build up in the control chamber, which in turn is going to open or close the discharge valve. So that isobaric capsule is constantly expanding, contracting, regulating the pressure in the pressure controller, and by regulating the pressure in the controller, that in turn is talking to the discharge valve and telling it to open or close to regulate the amount of air that's being allowed out of the cabin, and that is going to maintain the cabin air at the selected rate of change. Yeah, so once we've reached our altitude, the rate of change is now balanced, and it's the isobaric capsule that is controlling. And that condition will exist until the cabin altitude reaches the controller setting. Conditions will stabilize, the discharge valves will open and close to maintain the pressure, and that is known as isobaric control. Does that make sense to you?
Yes, Jim. And this is discharge valve charging and discharging. This is during the descent or ascent. It's what happens when the aircraft is level in cruise.
Yeah, the isobaric is when it's in cruise. The rate of change is saying that we want to allow that cabin pressure to change at a rate of 300 feet per minute. Yeah, so by setting this up, it's allowing the air to escape, so the air is changing in the cabin. That cabin altitude is changing at a rate of 300 feet per minute, even though the aircraft is climbing at 1,000 feet per minute.
So is it while climbing?
The rate of change, yeah, is while the aircraft's climbing. We set the rate of change up, yeah. So we want to climb the cabin at a rate of 300 feet per minute, yeah. And the way the controller acts is talking to the discharge valve. So the discharge valve is allowing air out at the equivalent rate, you know. So what we don't want to do is pressurize the cabin to 8,000 feet instantly. Yeah. So what we need to do is to do it gently. And the controller is making sure that the discharge valve will allow the air to escape at sufficient rate so that the pressure in the cabin is built up to 8,000 psi over a period of time. Yeah. The altitude controller is making sure that when we reach the cruising altitude for the aircraft, that the discharge valve is now set to relieve that pressure at the rate required. So we're not needing to change the pressure in the cabin. We need to maintain the pressure in the cabin, and it's the isobaric capsule now that takes over, and it maintains the cabin pressure until we decide that we want to change the altitude of the aircraft. changing the altitude of the aircraft. Yeah. Now we're going to set the rate. How quickly do I want to change it? Right, we're going to descend. So I want the aircraft to descend at 900 feet per minute. I want the cabin to descend at 300 feet per minute. Yeah, so I'll set that rate of change. And again, that rate of change will act on the discharge valve so that the cabin pressure is being reduced at a nice steady rate. You see that?
Hello, Jim.
Hello.
This discharge valve is outshell valve itself. Am I right?
The discharge valve what?
Is outflow valve.
Yeah.
Okay.
Yeah, it's the same thing. The outflow valve and the discharge valve do the same thing. We just call it a discharge valve. It's in the pneumatic system, and that's the old name for it. The outflow valve tends to be on the more modern aircraft where it's an electronic system, but it's doing exactly the same job.
Okay.
Yeah. So what we need to know out of all that lot, like I said, I didn't want to get too deep into it because it becomes a chew. But the isobaric capsule, once the aircraft is at its selected cruising altitude and the cabin is at its selected cabin altitude, that isobaric capsule is doing a balancing act, and it's making sure that the cabin pressure is maintained at the right altitude. Yeah. If we want to change the cabin pressure, then we need to change the altitude and how quickly we want that to change. Yeah, so it all becomes a balancing act. Yeah, so cabin air allowed to exhaust via the discharge valves, slightly higher rate than it's being supplied by the blowers. Allows the pressure within the cabin to decrease relative to airfield pressure, increase relative to the outside pressure. As the aircraft climbs. Condition will exist until the cabin altitude reaches the controller setting, when conditions will stabilise. The discharge valves will open and close to maintain the pressure equivalent to that controller setting. That is our isobaric control. Okay. So I've set the controller to, was it a cabin altitude of 8,000 feet. Yeah, I've set that. The rate of change, 300 feet per minute, and it's the change in pressure in the pressure controller that is allowing the air from the cabin to escape. Once we've reached that 8,000 feet, yeah, the rate of change controller is set, and the pressure in the pressure controller is balancing the pressure to the discharge valve. Any slight changes in pressure, yeah, it's going to cause the discharge valve to open or close, and that's regulating the outflow, maintaining the cabin pressure at the set value. Yeah, so again, aircraft reaches its cruising altitude, levels out with the cabin at 8,000 feet. Pressures acting on the diaphragm equalise. After this, the combined action of the isobaric capsule and the control valve ensure that constant pressure signal is passed to the discharge valve. So we're maintaining the cabin altitude at the set level by that isobaric control, and that is the term that you need to remember. Is everybody okay with that?
Jim?
Yeah.
And the pressure control in the pressure controller, the altitude controller, is it the cabin altitude controller or landing field elevation controller?
It's the cabin altitude controller.
Okay.
But this is what we're saying. When the pilot is doing his his checks, he knows what altitude that the airfield he's landing at is going to be. Yeah, so he will set the cabin altitude to the correct altitude for the airfield that he's landing at. Yeah, so that the cabin rate of change, yeah, we'll set that as well, so that the aircraft descends, the cabin pressure is changing at the correct rate, so that the cabin pressure and the ambient pressure will meet at the correct point in time. Let's just go back a couple of slides. Yeah, going to take off. Let's just say we're going to, I don't know, think of an airfield where you are. Lucknow, maybe a bit small, but what nice big airfields have you got apart from Kathmandu?
Bhairava, Pokhara.
Pokhara. Okay, we'll fly there, and let's say that we're going to cruise to Pokhara at 25,000 feet. The aircraft is going to climb. Yeah, we'll take off from Kathmandu to Pokhara. We're going to climb the aircraft at a rate of 800 feet per minute. Then we're going to get to 25,000 feet, and we're going to cruise along. Yeah, what I want to do is to change the pressure in the cabin at a much more comfortable level. So I'm going to change the pressure in the cabin at 300 feet per minute. So on the pressure controller, I will set up a cabin altitude of 8,000 feet. And I will set up a rate of change at 300 feet per minute. And the idea is that as the cabin altitude reaches 8,000 feet, yeah, the rate of change is going to make sure that the cabin gets to 8,000 feet as the aircraft, or just prior to the aircraft reaching its cruising altitude, 25,000 feet. So we've set that up, and the pressure controller is talking to the discharge valve, and it is regulating the pressure buildup in the cabin. Yeah. So as the aircraft is climbing, yeah, the altitude outside is getting lower and lower. The pressure outside is getting lower and lower. Yeah. What we want to do is to make sure that the pressure in the aircraft, once we get to 25,000 feet, outside air pressure of 5.5 near enough psi, we want to maintain the cabin pressure at 10 psi so we can breathe. So as the aircraft's climbing, we're changing the cabin altitude slowly. Then when we get to that 8,000 feet point, yeah, now we're going to the pressure controller is going to maintain that 10 psi, maintain that 8,000 feet setting, yeah, all the way through the cruise. That cabin is being controlled by the isobaric capsule, so it's isobaric control. Yeah, that's allowing air to build up and escape from the cabin, and by balancing it, we're maintaining that just for argument's sake, 11 psi pressure in the cabin. So as we go on to Pokhara, yeah, we're cruising. Pokhara, let's say it's a slightly higher altitude of what? 13,000 feet. Yeah. So as the aircraft's descending, yeah, now what I want to do is to change the pressure in the cabin and control the rate of change of cabin pressure. So as the aircraft reaches the airfield landing height, the cabin pressure equalizes to the ambient. Yeah, and I do that just by setting the controller. Yeah, so set my cabin altitude. Yeah, set the rate of change that I want to however many feet per minute. Yeah, And away we go. Yeah. But it's the isobaric bit that you guys need to worry about. Don't, apart from your own interest, don't worry about how the things operate and what the different valves are doing. It gets a bit boggy. But all that's happening is we're taking pressure in from the cabin in that top chamber. It's looking at what height we've got. We're setting up how quickly we want the air in the air pressure in the cabin to change, and it's doing that by opening and closing the discharge valve. So now, as the aircraft's climbing, the pressure's changing, and the discharge valve is allowing that pressure to change at a controlled rate. Once we've achieved our cabin altitude, the rate of change has finished. We're at the selected altitude. So now the pressure above and below the diaphragm is equal. Any changes will be felt on that isobaric capsule. As that senses the changes, again, it's just opening and closing a little valve, which in turn is changing the pressure at the discharge valve. As the pressure at the discharge valve changes, that's again regulating the outflow of air from the cabin. Is that okay? Any questions there?
Jim.
Yeah.
When we press the depressurizing solenoid,
yeah,
cabin air is dumped via discharge valve, or?
Yeah, it goes out via the discharge valve. What you're doing with the depressurizing solenoid, you're taking away the pressure from the. Are you allowing pressure into the? Taking away pressure from the top of the chamber, which is opening the discharge valve, and so all the cabin air is going to escape. Yeah, so by allowing all that cabin air out, you're now equalising the pressure from ambient to inside the cabin. Yeah, so your depressurising solenoid is just opening the discharge valve fully.
Okay.
Yep. Anybody else? Any questions on that little lot? Yeah, on landing, discharge valves are opened via the depressurising solenoids. That relieves any residual pressure that's in the cabin, equals everything out. If they've got them fitted, the dump valves then selected open. Again, that's just a safety thing. Make sure that there's no residual pressure in the cabin. Yeah, I can't think of anything else to say there. Just what's going on in the pressure controller. We don't need to worry about that. Yeah, and again, that's just showing us what's going on. But, again, I'm not gonna worry about that too much. We've got a good idea. The thing that you guys need to remember is the isobaric control. Yeah. And then the little graph that we talked about, just showing us that we're going to set the cabin rate of change to marry up with the actual aircraft. Yeah, so we set up 300 feet per minute, so cabin altitude 8,000 feet. So as the aircraft reaches its cruising altitude, or just prior to that, and the cabin is at its set level, isobaric control until we change again. And we can set the rate of descent so that just before we reach the selected altitude, the aircraft and the cabin pressures are the same. Yeah, differential capsule in the pressure controller, just another valve in the pressure controller, ensures that the maximum differential pressure is not exceeded. Yeah. In the event of the pressure controller failing, each discharge valve has got built-in safety relief valve. Opens the discharge valve at a pressure slightly above the differential capsule setting. Should the complete system fail, the safety valve that we mentioned on the rear bulkhead, that's an additional, it's a pressure relief valve essentially, that's going to operate. The safety relief valve will operate at a slightly higher pressure than the discharge valve set at. Yeah, discharge valves also will allow an inward vent if we get a negative differential pressure. All that's just it's just showing the operation of the valve. So as the valve lifts, yeah, it's just showing how it's pushing up on that cap and allowing the valve to open. Yeah, as the pressure above pushes down, it's just going to close it off. The other thing that we have somewhere is a ditching handle. In the event of the aircraft having to land on water, yeah, we've got the ditching handle. Just a cable down to the discharge valve, pulls up on the handle, and it allows the outflow valve to close, prevents water from getting into the cabin. Yeah. Operate the ditching valve. It allows water to enter the discharge valve body, and by allowing that water into the body, it keeps the discharge valve closed and prevents water from flowing up into the aircraft. Do you all remember the aircraft that crashed on the Hudson River? Yeah, New York. It landed on the Hudson River. Chelsea.
Yes, Jim. There's
Sully.
Yeah.
There's a movie on it.
If you ever get the chance, watch that. It is fantastic. It looks like it would be the most boring film ever, but it isn't. It's really, really good. And one of the things that they tried to get Sully for, I mean, he went through all that. He landed the aircraft. He landed it perfectly on the water. Everybody got out. Nobody was injured. Nobody died. And one of the things that the company tried to do him for was not operating the ditching valve. The aircraft floated anyway, but the ditching handle, he forgot to pull it, and that was one of the things that they tried to do him for. But I strongly recommend, if you ever get the chance to watch the film Sully, Tom Hanks, he never makes a bad movie, and Sully is really good. I thought it'd be awful, but it wasn't. It was a really good film. Yeah, there's nothing else in it. So there, yeah. So pulling the ditching handle seals the discharge valve, allows water to flood the body, and by allowing water to flood the body, it seals it off and prevents anything from getting into the cabin. Again, there's the little picture from your notes. Yeah, slightly different to the one that we've just seen, but works on the same principle. Filter allowing cabin air in. You've got your isobaric control, which is doing its balancing act, and that balancing act lifting and closing the outflow valve, which in turn is allowing cabin air to be released gradually. Yeah, we don't want to burst the aeroplane. Anybody got any questions on that? Ditching control, yeah, pull the ditching handle, water floods in, yeah, fills the chamber. Because it's filling the chamber, it pushes that valve down. Pushing the valve down seals off the outflow valve. If we get a negative pressure, will act on the inward relief valve. As it acts on the inward relief valve, it's opening the outflow valve or the discharge valve to atmosphere. Yeah, just we have the pressure controller where we've looked at all that. We'll just have a look at the indications that we're gonna have, and we've got a digital version as well. We'll look at digital in a minute. The digitals are a lot better. Yeah, cabin altitude, rate of change. Yeah, you got your maximum differential. Yeah, and again, yeah. Landing altitude, so you can select your change there as well. So indications that we need: a cabin altimeter, a rate of change indicator, and a differential pressure gauge. Those are the three indications that we want. Yeah, top of page 30. Again, stick a highlighter through those. They're the same for all the pressurization systems. Yeah, what we need is the cabin alt, the rate of change, sometimes called the vertical climb indicator, I think, and the differential pressure gauge. Cabin altimeter, differential pressure gauge, normally combined, as we saw earlier. Both cabin and atmospheric pressure supplied to the instrument. Rate of change indicator, yeah, we've said that, nothing to worry about there. Cabin altitude warning light fitted, and that cabin altitude warning light, I think we come on to that in a minute, but the cabin warning light will come on when the cabin altitude reaches 10,000 feet. Yeah, that will put on a warning light in the cabin. Yeah, if the cabin altitude set, if it exceeds 10,000 feet, we'll get the warning light. We'll get the warning light because it means we need to provide the passengers with oxygen. So 10,000 feet for the warning light. I think we come on to that later on this afternoon as well. Yeah, the electronic system is a lot better. Yeah. The automatic system, yeah, the cabin altitude controllers are duplicated, and the cabin altitude sensors are looking from different inputs. Yeah. The altitude controller, yeah, all electronic. It's taking in information from the air data computer, the cabin altitude controller, different systems in the aircraft, it says. That produces a reference signal which is used by the altitude controller and the altitude monitor. And the two are looking at each other to make sure that the cabin altitude is maintained within the correct levels. It goes through the setting up of the thing. I'll run through that quickly on the slide. Nothing for us to get too fretful about. Yeah, so we're taking off from an airfield at sea level. Yeah, we're going to cruise at 43,000 feet. The landing airfield, 4,000 feet altitude. We're going to set up the maximum altitude, yeah, which is our 43,000 feet. We'll set in the landing field elevation. We'll set up the rate of change. Yeah, in this case, it's 500 feet per minute, and then 300 feet per minute on the descent. We've got that all set up. Yeah, we're sitting at sea level. The doors are open. Yeah, no differential pressure. Turn on the air conditioning system, the air system. Yeah, close the doors, and now pressure is going to start to build up. But it's only going to build up by a very small amount, and the reason for that is to make sure that everything, all the valves in the system and the controllers are all set up. Yeah, that they're all stabilized and ready to go. Yeah. Go off to taxiing, yeah, and then as we wallop off down our take-up run, yeah, the pressure starts to increase a little bit. Yeah, the wow switches kick in as the aircraft takes off, and then at the selected climbing altitude, the aircraft starts to climb. From that point, the cabin controller, is changing the cabin altitude at a rate of 500 feet per minute, which is what we set. Yeah, and as the aircraft reaches its cruising altitude, the cabin reaches its selected altitude. From there, as the aircraft's cruising at 43,000, yabba dabba do, the cabin is maintained at, it says in this case, 6,000 feet. A lot of the more modern aircraft, because of the volume of air that we're providing, we can go up to 6,000 feet without causing any discomfort. So we're going to maintain that isobarically, that isobaric capsule, but within the digital controller. Yeah, it's monitoring what's going on. It's adjusting the outflow, from the cabin and keeping us at the selected cabin altitude. Just prior to the aircraft descending, then the cabin descent's going to start, but the cabin descent's going to be at a controlled rate of 300 feet per minute. The aircraft is going to start descending towards whatever the airfield is. Yeah, as we get to the landing point, the cabin pressure and the ambient pressure should be the same. And in this case, I think we said 500 feet above sea level. Yeah. So sorry, 4,000 feet above sea level. What we're going to do is set the cabin pressure slightly below that, and what that's doing is ensuring that there's no residual pressure left in the cabin. It's all discharged. Again, as we taxi in, the aircraft's going to have that slight pressure differential just to make sure that all the valves and everything are reset. Turn the air off. Yeah. Open the doors, and everything should be nice and even Stevens. If you are working on any pressurized aircraft, what I'd say at this point, and certainly on large aircraft, there is a procedure that you've got to follow before you open the doors, and that procedure is there to ensure that all the cabin pressure has been dissipated before you open the door. If you don't follow that procedure, you're going to end up with a big fat hunk of metal cabin door smacking into your face, and that will hurt. And so one of the things we've got to ensure is that all the pressure has been dissipated. Yeah. Controller itself, you've got your two controllers, and the two controllers are monitoring the various inputs. From the altitude controller, what you set your rate up at, whether you're in auto, manual, which controller's got primacy. The controllers are looking at that. If you get a failure in one, the other will automatically take over. They're looking at the position of the wow switches. They're looking at the altitudes that have been set up, looking at the position of the throttles or the thrust levers, and they're monitoring the cabin pressure at the same time. The controllers, working the outflow valves. The outflow valves operated by little electric motors. So the electric motors operate in the position of the outflow valve, and the rate is what we've set up on the control panel. So we set up the brains of the outfit, shuntering away, monitoring what's going on. And again, that's sending signals down to the outflow valve. The outflow valve opening and closing, regulating the flow of pressure out of the aircraft. Pressure relief valve, if we have a failure in the system for whatever reason, if the aircraft overpressurizes, there's the safety valve there. And likewise, when it talks about the vacuum relief, that's just the inward safety relief valve. Again, your indicators that we talked about before. Yeah. So the schedule that we'll just go through that. Pre-pressurization of the cabin is required prior to takeoff. Pressure controller requires inputs from the landing gear, engine oil pressure, throttle position, and the door warning system. It needs to know what position the doors are in. Cabin pressure marginally above ambient. Yeah, and that pre-pressurization schedule is there to ensure that the controller, the outflow valves, are all stabilized, and when the aircraft takes off, everything will kick in nice and smoothly. Yeah, off into the climb, aircraft leaves the ground, the WOWs turn over, or the squat switches if you're American. The cabin altitude climb sequence now commences, and the cabin altitude rate of change is what's set up, but that's limited to around about 500 feet per minute. Yeah, these pictures, they're not very clear, but they were taken from a 747. The pilot, friend of one of my students, took them for us. And as you can see, the aircraft altitude's changing. Yeah, the aircraft's climbing. And I don't know whether you can see it very clearly, but the cabin altitude here, yeah, set up. We've got the differential pressure showing, yeah, and away we go. So this is climbing at 300 feet per minute. We've got to 12,000 feet actual height. The cabin altitude has changed to 5,600 feet. Aircraft gets up to 33,000 feet, 33,500 feet. Yeah, the cabin altitude is now 63,000 feet. And the rate of change is now slowing up because we're coming up towards our cruising altitude. So the rate of change is now 100 feet per minute. You can see on there as well, just as an aside, when we were talking about the supply side of things, and we said we could monitor the duct pressure, and again, it's showing the crew what's going on in the duct. So if there was any fault there, it would be quite noticeable. Reach our cruising altitude, 39,000 feet. Got to 39,000 feet. The cabin altitude is stabilized at 6,300 feet. Yeah, there's no rate of change because we are where we are. Yeah, the duct pressure has dropped because the feed into the cabin is reduced. It's not required to be so great. And now that isobaric control will keep the cabin altitude at 6,300 feet until something changes. Yeah, so sitting in the cruise, the aircraft maintain a constant height. Cruise sequence kicks in. Cabin altitude controller, yeah, will look for any change in the cabin altitude compared to the aircraft altitude. Any variation to aircraft altitude in climb or descent of less than 500 feet results in the cabin altitude staying the same. If there is a change in altitude of more than 500 feet, then the altitude controller will adjust the cabin altitude accordingly. So it may be that we've hit a bit of turbulence and air traffic have said climb to flight level whatever. Yeah, as the aircraft ascends, as it goes up, the controller will automatically change the cabin altitude. It will compensate as we go through, as we pass 500 feet. If we descend through 500 feet, then the cabin controller will start the descent procedure. Yeah, so it's monitoring everything that's going on. Any change by more than 500 feet, the controller will look at that and it'll change the cabin altitude accordingly. Yeah. Start the descent. Yeah, as we go down through 500 feet. Yeah, the schedule will start, but again, it says it depends on certain factors: the altitude, cabin altitude, the auto rate of change, landing airfield height. It'll look at all those parameters and it'll adjust the cabin altitude accordingly. Yeah, as we come into land, yeah, for those aircraft designed to land in a pressurized condition, the altitude controller will normally automatically lower the landing field height by approximately 100 feet. By lowering the landing field height by that 100 feet, it ensures that there is a small amount of pressure left in the cabin. So the cabin will remain slightly pressurized above atmospheric until we've touched down. Once we've landed, the wows will allow everything else to open up and that residual pressure to escape. Protection, yeah, is by duplication. In the event of a system or power failure, control automatically transferred to the standby system, which is electrically supplied from an alternate source. So it'd be a different power source. If total system failure occurs, we've got the option of manual reversion. And in that case, the outflow valve is going to be positioned by the pilot. Yeah, so he is going to, if he's in manual, he's going to be adjusting the position of the outflow valve as the aircraft is descending. Don't forget with this lot, you know, if you lose your cabin pressurization, you've got to get the aircraft down as soon as you can. So we've got breathable oxygen in the atmosphere. Anybody got any questions on the electronic side of things? Deathly silence. That's fine. What I'm going to do, just let me have a look in the notes here, make sure I missed anything. So we talked about pre-pressurization. Yeah. Talked about the climb, get the aircraft up. Sitting in the cruise, isobaric control. Yeah, start to descend. Yeah, once we go through 500 feet, the thing will start to automatically bring us in. Landing, slightly lower than the airfield landing height to make sure that we keep a little bit of pressure. Yeah. Anything else? The outflow valves, electrically operated. Just that door that opens and closes. Electrically driven actuators. One at a time. Blood from the engines. Yeah. Automatic relief valve. Form of discharge valve used on some aircraft types. Additional to the discharge valves. Operates when the aircraft's on the ground. Allows free-flowing air within the aircraft when we're parked up. Prevents cabin pressurization when the aircraft's taxiing. And controls the pre-pressurization. So the ground relief valve, just there, as the name suggests, while we're on the ground, keeps the system open to atmosphere, allows vent air to circulate, and it allows that air out to atmosphere. So when your air conditioning's running, yeah, there's no sort of pressure build-up while we're on the ground. Yeah. And it controls the pre-pressurization cabin before takeoff and when we've landed. Yeah, so as the relief valve opens, then the cabin's going to be open to atmosphere. Yeah. Safety protection system, 2 safety relief valves. Safety relief valves pneumatically operated, totally independent of the pressurization system. So it's basically a pressure relief valve that's fitted on the bulkhead. If the pressure becomes too much, the relief valve will open. Inward relief valve is your negative pressure. Yeah, so if we get that negative differential of, I think we said 0.5 psi, yeah, the inward relief valve will open. And again, exactly as we saw before, the cabin altitude system If cabin altitude exceeds 10,000 feet, we'll get a warning light on. Yeah. And that'll give them whistles and bells as well. Indicators. Instruments. Anything I need to say there? Not really. Yeah. Cabin halt, rate of change. Yeah, that rate of change, sometimes called the vertical speed indicator. So just be aware of that. I don't think it's a question, but if you see vertical speed, it is the rate of change. And that, again, in the notes was our valves. Nothing there that we need to worry about. Nothing there we need to worry about. I'm just slightly ahead of the game here, but we didn't have the 10 minutes that we normally have, otherwise it'd have been smack on. So the chances are we'll finish a little bit early for lunch, mainly because we didn't have the 10-minute screen break, and that is my fault. That's my bad. I do apologise. If you guys need a break from this, please shout up. Yeah, because I just start rabbiting on. My head's in 1,000 places all at once, and I tend to forget things. So if you do need a break, just say, Jim, can we have 10 minutes? Can we have 5 minutes or whatever? Don't be shy. Shout up.
No, we can have for lunch only.
Okay, right. I'll finish this off, and then we'll have we'll add that
Yes, sir,
10
we can
minutes to the lunch break.
It is okay. You can forget everything, but just don't forget the important part.
Yeah,
highlighted part.
Yeah, that's why I'm reading through the notes at the same time, just to make sure that we're all getting the right information.
Because we do have 4 questions from pressurization system, right?
Sorry?
4 questions coming from pressurization system.
Yeah. Yeah. Yes, there is. I'm just trying to think. I think the lines are on about isobaric control. I've definitely seen that one. Indicators. I'm pretty sure I've seen what are the indications that are required. And I'll have a look at lunchtime and see if I can think of anything else I recognise.
Excuse me, Jim.
Yeah.
What type of question will come about the isobaric control? Can you tell me the question?
No, I can't, because I don't know how it'll be worded, but it'll be something along the lines of how is cabin pressure maintained when the aircraft's at cruising altitude. Yeah, it'll be something along those lines.
Okay, sir. Better you give, if 4 questions are coming from pressurization, you give 8-9 questions. Out of that question only it will come, then it's better for us.
I didn't catch a word of that, sorry.
If the 4 questions are coming from the pressurization system,
yeah.
If you give us 8-9 questions from this system, then it's easy for us to remember.
Yeah, I'll send out some questions again either tonight or tomorrow.
About among them, it will only come, Jim.
Eh?
Among them, only the question is come, whichever the question you are giving us, from that only it will come, or from other part.
I'm not with you there. What I'll do, exactly as I've done right the way through, I will send you a series of open questions that will help you revise the subject so you can understand the subject, and it will give you an idea of where the area of the questions, yeah, which is what all the questions I've sent you so far have been designed to do, designed to help you out. But as I say, I'm not prepared to coach you. I'm not prepared to say this is definitely an exam question. You need to understand the subject. I can, like I said, when we were talking about the controller, you don't need to know the internal workings. I can tell you that, but you do need to know what that controller is there for and what it's doing. Yeah, and also because you've got the notes, I am duty bound to go through and explain the contents of the notes to you, but I am not prepared to coach you for the exam. That serves no purpose whatsoever.
Okay, thank you, Jim.
Okay?
Yes, sir.
Right, so pressurization systems, yeah, we need to test them every now and then. So we're going to check that there's no leaks in the system, that the airframe isn't leaking, that the controlling equipment and everything's working correctly. Yeah. Those periods when we're going to test are specified in the maintenance manual. And it's also if we have a major repair or a modification, yeah, or if there's been damage to the structure, we might need to carry out a pressure check there. Yeah. So, yeah. Oh, the reason the Helios aircraft is there is long time ago, a few years back now, the ground crew had been investigating a pressurization problem on this particular aircraft. And part of that pressurization test was to move a switch from aircraft system to maintenance. And when they were doing the tests and everything, they did not reset the switch from the maintenance position. Subsequently, the aircraft took off, and as it had a nice gentle rate of climb, the cabin wasn't pressurizing, and because the cabin wasn't pressurizing, the crew started to suffer the effects of hypoxia. They didn't realize it was happening. The aircraft reached its cruising altitude, all on the automatic side of things, but the cabin hadn't pressurized. The crew suffered unconsciousness. They all fell unconscious, and the aircraft just carried on its automatic settings until it went into the descent mode. And as it went into the descent mode, it went into the side of a mountain. Yeah, and that was all because the guys hadn't followed the procedure and hadn't reset a switch in the cabin. So when you do these checks, it's vital that you make sure you know what's going on, what you're doing. Things that we need to know, yeah, the structure of the aircraft has got to be complete and fit for flight before we carry out any ground test. Anybody that's in the cabin must be medically fit and must be free from colds and sinus problems. Because you are getting a differential pressure, if you've got a cold, yeah, you could pop your eardrums. Anywhere where the pressure differential between the cabin and ambient exceeds 10 psi, then you've got to have medical supervision. You've got to be signed up by the medics to say that you are fit to go into the cabin for that test. Worth whacking your highlighter through the fact that a minimum of 2 test operators should be inside the pressurized area when we're doing a pressure test. Where we're using an external ground supply. If we're using engines for doing a pressure test, then we need a 3rd operator in the aircraft to run the engines. Yeah, so you're going to have a minimum of 2 inside external rig, 3 if you're using the engines. Anybody inside and outside the aircraft has to have communication, so you need headsets, long leads, all the other good stuff. Pitot-static connections have got to be connected. Pitot-static system intact. Don't forget that you are replicating change in altitude, so the pitot-static system is going to be infected. Likewise with certain of the instruments, because you're on the ground, so ambient pressure is going to be 14.9 psi. The cabin pressure is going to be changing. So the cabin pressure is going to be reducing in regard to ambient. So certain of the instruments need to be removed or blanked before we carry out our pressure test. Must not exceed the cabin differential rate of change. Any disturbance of the cabin air ducting has been carried out, then we need to make sure that we leak check and all the good stuff on that. Seals, glands, expansion joints, make sure that they're all correctly fitted. Don't seal anything with jointing compound. That's just common sense. Once you've done your pressurization checks, make sure that all your windows, doors, hatches are checked for serviceability. American aircraft, it was a fuel tanker. Again, they were pressurizing the aeroplane and they screwed up, and that was the result. Your cabin leak tester, connect that to the aircraft, and what we're going to do is pump pressure into the aeroplane. As we build up that pressure, we're going to check that the relief valves are working, the outflow valves are working, and then one of the things we do, we'll put a certain amount of pressure into the aeroplane, and we'll turn the rig off, and we measure the rate of time it takes for that pressure to leak out. There is, for most aircraft, a designed leak rate, so we just monitor how quickly that comes down. We can run the engines, we can connect a supply unit, we could use the APU for carrying out our checks, but it's recommended that the engines are done. However, we always used to use a test rig because it was a lot safer. I can't say much more than follow the AMM. Any internal doors need to be secured and latched in the open position. Cabin doors for carrying out your pressure checks need to be in the closed position and checked that they're not gonna pop open. Any unpressurized areas vented to atmosphere, so if you do get an escape of pressurized air, it's going to escape. Follow the manual is what we'll say there. But the aircraft fit for flight before we carry out any checks. You've got to be medically fit and free from colds and sinus troubles. Warning placards around the aircraft when you're carrying out the test. All pitot-static connections connected. Other stuff we've already talked about and said. Following completion of tests, windows, doors, all check for serviceability. Make sure that they've not been distorted by the pressure check. Unless otherwise stated, we said that all doors and hatches in the pressurized area secured in the open position. After entering the aircraft, entrance doors, emergency exit hatches, all the rest of it, all closed and locked. Specified in the manual, toilet vents, bleed air outlets, all that sort of thing need to be blanked off. So you're actually getting pressure in there. You're not just pushing it back out to atmosphere. Rate of change, doesn't exceed that specified. Checking the rate of change. Pump the cabin up. Make sure it stabilizes. Make sure that isobaric control's working. Then again, following the manual extremely closely, we can increase the pressure and make sure that the safety relief valves operate. Yeah. That's our leak rate test. Yeah. Again, following the manual. Ding, 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 ding. Nothing there that we need to worry about. Yeah, that last bit, page 42. There's not a question, but before you open any windows or doors or hatches, again, make sure that the cabin pressure has been relieved, so you're not going to open a door into anybody's face. Yeah, can't see anything there. The electronic control, yeah, we're just doing the same thing, but checking all the valves out. The leak rate tests, carry those out at specified periods, and it just makes sure that the cabin seals are all working. We'll pump it up to the required pressure, turn everything off, and then just see how quickly that pressure drops. The proof pressure check. Yeah, proof pressure check is definitely worth a highlighter. Yeah, that's carried out during manufacture and maybe carried out after any major repairs or modifications. And the proof pressure test is carried out at 1.33 times the maximum operating differential pressure. It's a bit like our ultimate load, but for pressurization. Yeah, so the proof pressure test, we're going to pressurize the aircraft to the maximum operating differential pressure and then increase it by 1.33. Yeah, the proof pressure checks are carried out by a remote external supply rig and gauges, and nobody is allowed in the aircraft while we're doing proof pressure checking. Yeah, special safety valve fitted to preserve the aircraft structure if anything goes wrong. And with the proof pressure test, we'll put it up to pressure. We'll hold that pressure for 1 minute and then bring it down to the acceptable level. Yeah, so your proof pressure check, make sure you highlight that one, page 43. Yeah, the other thing, the last bit, when you're carrying out sorry, I've lost my bloody. I've lost my thingy. There we go. Yeah. Yeah.
Hello,
when.
Jim.
Yeah. Sorry. Just bear with me. I'm just trying to get my thing back. Yeah. Last bit on page 44. When ground testing a pressure cabin, yeah, the differential pressure increases, the cabin rate of change indicator will show a rate of descent. Yeah, so all the controls from the ground test, make sure that they are reset to the right position prior to flight. So you think about it, yeah, because you're at ground level, yeah, you're pressurizing the cabin, the rate of change indicator is going to show you descending rather than climbing. So again, watch for that one. The note at the bottom of page 44. Right, somebody was shouting at me. Sorry, who be that?
Jim, I didn't get this note.
What note?
When ground testing a pressure cabin, as a differential pressure increases, the cabin rate of change indicators will show a rate of descent. That is okay. I understood that. Ensure all controls are reset from ground test to the correct position required for flight.
Yeah. So when you're carrying out your checks, some aircraft have a switch for ground testing, and what that does is it protects certain instruments and what have you from being damaged during the test. That was what I was saying about that Helios aircraft. Yeah. So they went from the ground test position. They didn't reset. So everything was out of sync for flight.
Okay, okay, I got it, Jim. Now I got it.
Good.
After ground test, it should be reset again for flight.
Yes.
Okay.
And obviously, if you follow the steps in the manual, that shouldn't get missed. But it's just something to watch out for.
Thank you, Jim.
Yeah. But for our purposes, yeah, make sure that when you're ground testing, yeah, the differential pressure is going to increase. The cabin rate of change indicator will show a rate of descent. Yeah, and that sometimes crops up. So from there then, guys, yeah, we've had a look at how we're going to supply the air. Yeah, we went from our engines, we went through the pre-coolers, off of the system, yeah, into the cooling packs. The cooling packs sending up the air to the mixing manifold, and that air from the mixing manifold we're going to pump into the cabin. As we pump it into the cabin, yeah, relative to the ambient air, we're going to take it up to a controlled rate. We're going to take it up to a selected cabin altitude. That selected cabin altitude is going to be controlled by the outflow valve. The outflow valve modulating, and it's going to keep us at the right cabin altitude until we start our descent. And again, the thing's going to change. So, aeroplane, not a very good aeroplane, but yeah. Pressurizing, we've got the outflow valve. Yeah, so air being pushed in via the hat racks and everything. That air has got to come out, otherwise we just carry on blowing up and blowing up and blowing up like a balloon. So if you blow a balloon up and you hold the end, yeah, you can let the air out at a controlled rate by squeezing the inlet to the balloon. And it's the same with our aeroplane. Yeah, we're pushing this air in and we're just opening and closing that outflow valve, and that's regulating the flow of air out. Yeah, what we're going to do is slow down that rate of escape until we reach the selected cabin altitude. As we get to the selected cabin altitude, the isobaric control is going to modulate the opening and closing of the outflow valve, the discharge valve, to maintain that pressure within the cabin. The difference between the two, it's the aircraft structure that limits the differential we've got. Don't forget the three maximum differentials that we talked about, the 8 to 9 for your jet aircraft, 5.5 for your turbine propeller aircraft, and what was it, 4.5 for your twin engine turboprop. So we've got the differential pressure, yeah, how we're going to pump in. The indicators, yeah, we talked about those, the three different indications that we get. The cabin altitude and I think it was the differential pressure can be on the same gauge. Just double check that one, make sure I'm not giving you the wrong ones. What else did we talk about? What else can we have? Just trying to think there. Yeah, the two types of controller, isobaric control, electronic one, taking in information from all different places. That's got its own little schedule. Pressure checks and the proof pressure test, 1.33 times the maximum differential pressure. Again, we're making sure that the structure is strong enough to hold it. And that, guys, was our pressurization. Has anybody got any questions at all on the pressurization side of things? No. All quiet. Right. This afternoon, we'll have a look at the oxygen side of things then, oxygen systems. So I'll see you back at the usual time, 12:15 my time. I think that's 1900 your time, isn't it?
Okay, Jim.
Okay. If you do think of any questions, we're flying at altitude. We said we're going to pressurize the air. And by pressurizing the air, we're simulating the atmosphere at a lower altitude. And in the lower altitudes, obviously, we've got plenty of oxygen. So if we get a failure in cabin pressurization, we need to carry some sort of emergency oxygen. Yeah, so make oxygen available for all the occupants of the aircraft until we can get the aircraft back down to a reasonable level. Yeah. So to ensure that, there are certain regulations that have been laid down and stipulated for all aircraft, and these regulations come down from ICAO. Yeah. All aircraft and operators shall ensure that passengers are made familiar with the location and use of oxygen dispensing equipment if the provision of oxygen for the use of passengers is prescribed. That means if your aircraft is going to be carrying passengers, they must be briefed on how to get that oxygen, where it's going to come from, and how you're going to use it, which is why you get the brief from the cabin crew in the unlikely event, you're all going to die. Oxygen will drop from the ceiling, pull the lanyard, and away we go. For non-pressurized aircraft, and that's an aeroplane intended to be operated at flight altitudes which atmospheric pressure is less than 10,000 feet, and personnel compartments shall be equipped with oxygen storing and dispensing apparatus. So your 700 hectopascals, 10,000 feet, the atmospheric pressure less than 10,000 feet. We've got to provide that oxygen. A flight operated at flight altitudes in which the atmospheric pressure in personnel compartments will be less than 700 hectopascals shall not be commenced unless sufficient stored breathing oxygen is carried to supply all crew members and 10% of the passengers for any period in excess of 30 minutes that the pressure will be lower, between 700 and 620 hectopascals, which is 13,000 feet. And the crew and the passengers for any period in that atmospheric pressure occupied by them will be less than 13,000 feet. So what we're saying in a non-pressurized aircraft, if we're going to go above 10,000 feet, then we have got to carry the oxygen on the aeroplane. If we're going below 700 hectopascals, so that is a lower altitude, we shan't commence the flight unless breathing oxygen is carried to supply all the crew members and 10% of the passengers for any period in excess of 30 minutes that the compartments are going to be at that low altitude. And above 13,000 feet, if we fly above 13,000 feet, we've got to supply that oxygen for the crew and the passengers, doesn't matter how long we're flying. Does that make sense to everybody? Good. That's one of your ICAO regulations. That's your non-pressurized aircraft. A sort of graphic, when we talk about the flight levels, we're talking about 10,000 feet, 14,000 feet, 15,000 feet. And roughly what it's saying is below 10,000 feet, we're not obliged to carry oxygen. 10,000 to 14,000 feet, we've got to carry enough oxygen for the crew, obviously, and any flight that's going to exceed 30 minutes, there's got to be oxygen for 10% of the passengers. 14 to 15,000 feet for 30% of the passengers, and anything over 15,000 feet, we need to carry oxygen for all of the passengers. The crew must have oxygen regardless. For our pressurized aeroplanes, airplane intended to be operated at flight altitudes at which the atmospheric pressure is less than 25,000 feet, or for which, if operated at flight altitudes at which the atmospheric pressure is more than 25,000 feet, cannot descend safely within 4 minutes to a flight altitude which is suitable. Then we've got to provide automatically deployable oxygen equipment. Total number of oxygen dispensing units shall exceed the number of passenger and cabin crew seats by at least 10%. All flight crew members of pressurized aeroplanes operating above an altitude where the atmospheric pressure is less than 25,000 feet shall have available a quick donning type of oxygen mask, which will readily supply oxygen, and we'll look at those in a minute. So pretty much, if we're going above 25,000 feet, if we can't get down to a suitable altitude, which is I think 10,000 feet, 14,000 feet, we've got to have automatically deployable oxygen, and that oxygen capacity has got to exceed the total occupancy by at least 10%. Flight crew, cabin crew, the flight crew have got to have a quick donning mask, which will automatically supply oxygen to them. So the two sets of regulations there, for non-pressurized aircraft and for pressurized aeroplanes. It talks about hectopascals. Hectopascals is a bit of a pain. It used to be millibars, but hectopascals taken over. Again, a quick graphic running around, for your 10,000 feet unpressurized aircraft. Anything up to 10,000 feet, no oxygen. Between 10 and 14, 30 minutes oxygen for all the crew, and up to 10% of the passengers. Anything above 14,000 feet, you've got to have oxygen for everybody. With your pressurized aircraft, if you can maintain your cabin altitude below 10,000 feet, swimming, nothing untoward there. At 10,000 feet, we'll get a warning light in the cabin. We discussed that this morning. If the cabin altitude goes to 14,000 feet, then oxygen will automatically be supplied for a minimum of 10 minutes for all the occupants of the aircraft. It says 25,000 feet, crew oxygen masks readily available, but that's a foregone conclusion. There will always be oxygen masks for the crew. Just for quick reference, when we're talking about hectopascals, 700 hectopascals is 10 psi, which is the equivalent of 10,000 feet in altitude. 620, 9 psi near enough, which is the equivalent of 13,000 feet. And your 376 is the equivalent of pretty much 5.5 psi, which is our 25,000 feet limit. So hectopascals is just a unit of pressure, and that unit of pressure equates to a particular altitude in the standard atmosphere, as we saw earlier. There's nothing there really for us to worry about. Just know that that's the ICAO regulations. And then those ICAO regulations are tweaked by the national authorities. In our case, it is going to be the CAA requirements. For CAA, read EASA. Yeah, Cap 393. Yeah, says that for pressurized aircraft, there's a requirement for crew oxygen at any flight above 10,000 feet. That's any flight above 10,000 feet. Pressurized aircraft. Yeah, the requirements for passenger oxygen, and we said if we go above 14,000 feet, then we've got to supply oxygen for 10% in excess of all the occupants. But an additional requirement for passenger oxygen depends on where that aircraft is operating. Yeah, whether the aircraft's cruising between 10,000 and 25,000 feet, or whether it's operating above 25,000 feet. You're probably well aware that your flight level 100, 10,000 feet, flight level 250, 25,000 feet. Yeah, in altitude. Yeah. The further variable that it talks about is whether the aircraft can get down to 12,000 feet or below, and the time it's going to take the aircraft to do that. That ability to get down is known as the minimum sector altitude. Yeah, so it kind of depends where the aircraft's operating. So let's say I am operating an aircraft in the let's say the Middle East. Yeah, and in the Middle East there are lots and lots and lots of areas of desert. And if I'm flying above that desert, yeah, if I have a major mishap, I can reduce the altitude of the aircraft down to, it says 12,000 feet or below, flight level 120 below. If I can get the aircraft down to that flight level within 5 minutes, yeah, I'm fine. I can go with the oxygen I'm carrying. If I'm flying, well, let's say out in Nepal, and I'm going up to, I don't know, India or somewhere like that, and I'm flying over the mountains, well, obviously, I can't get down to below flight level 120 within 5 minutes. And because of that, I need to carry additional oxygen equipment. Yeah, so the amount of oxygen to be carried and the proportion of passengers for whom suitable masks must be made available varies with the operating altitude, the rate of descent, and the minimum sector altitude that the aircraft is operating over. So let's say for certain aircraft, yeah, unless we can actually carry the required amount of oxygen, we've got to limit the route that aircraft can use. So it says for certain aircraft shouldn't be routed over higher parts of the Alps unless they can carry a mask for every occupant and the appropriate amount of oxygen. What that really boils down to is our passenger aircraft, part of the standard equipment is just to make sure that we have got plenty of oxygen. Yeah, so the aircraft can operate in all the different parameters. If for any reason the oxygen system is unserviceable or part of it is unserviceable, then we may well have to reconsider whereabouts we're going to and what routes we're going to use that aircraft on. So obviously over here, there's no way I can get down to the required level within that 5 minutes. So we need to carry the required amount of oxygen. Yeah. If you can't descend to flight level 120 or below within 5 minutes, the amount of oxygen in equipment is significantly increased. The amount of oxygen to be carried, the proportion of passengers for whom suitable masks must be made available, varies with the operating altitude, the rate of descent, and the minimum sector altitude. Yeah. So out of that lot, yeah, on page 7, you need to be aware that the ability of the aircraft to descend is dependent on the minimum sector altitude. So what the minimum altitude is in the area in which we're operated, and that is the land that we're flying over. Again, on bullet point 3 there, stick your highlighter through the fact that if the aircraft is unable to descend to flight level 120 or below within 5 minutes, we must carry additional oxygen equipment. Yeah. So the amount we carry depends on the area that we're operating in. Additionally, on top of that, we've got to provide first aid oxygen. Yeah, and that first aid oxygen has got to be able to supply 2% or 2 passengers, whichever the greater number, wherever they're seated. So to meet that requirement, we carry portable oxygen bottles, and those portable oxygen bottles carry sufficient amount of them to ensure that we can supply 2% of the passengers or 2 passengers wherever they are seated in the aeroplane. So you might have 2 at the front, 2 at the back, all having a heart attacks at the same time. We've got to make sure that we've got sufficient oxygen for them.
Jim,
Yeah,
what
the air navigation order, which is our CAP 393, requires operators give their operating staff sufficient information and instructions so that the scales of equipment are complied with on every flight. Yeah, so the company, yeah, whichever company you're working for, they've got to ensure that the operating staff for them know how much oxygen equipment we've got to be carrying, how much oxygen we've got to be carrying. Yeah, they've got to know the minimum acceptable oxygen contents or the minimum pressures of that oxygen equipment. The crews have got to know where appropriate to ensure that we can descend to flight level 120 within 5 minutes. And just want to note there, yeah, minimum acceptable oxygen contents or pressures, navigation procedures, and the MEL will detail any acceptable deviations from those requirements. So the oxygen equipment is dictated by the operator, or CAP 393 says that the operator has got to ensure that there's going to be sufficient oxygen. They do that by briefing all the staff and making sure that the staff know how much they've got to carry, what the minimum levels are, and if they're allowed to fly with anything unserviceable. If they are, that will be detailed in the MEL. Yeah, it's the operator's responsibility to make sure that the aircraft are correctly equipped for the tasks that they're being used. So any aircraft that hasn't got the right oxygen equipment must be, it says, restricted in its use. Yeah, we can only allow it to fly on certain heights, on certain routes, until that oxygen equipment is restored to its correct levels. Yeah. So MEL again is going to tell us any acceptable deviation from the regulations for carrying oxygen. Okay then, in our unpressurized aircraft, yeah, we're going to be carrying oxygen. That oxygen is stored in a pressure cylinder. Yeah, it's got an on-off switch, and that oxygen, once it's switched on, comes out as a continuous flow. Yeah, and the continuous flow system for small unpressurized aeroplanes, yeah, is very, very simple. It needs to be. There shouldn't be any dramas about it. Yeah, we've just got the bottle. We've got a distribution pipework. Yeah, and plugging in there, we've got pilot and passenger mask connections. Should we need to use oxygen in our unpressurized aeroplane, we can plug the mask in and breathe quite happily. So if I want to take the aircraft up to, I don't know, let's say 14,000 feet, let's say we're going flying over the Grand Canyon, Yeah, and we want to have a look around the local area. So to get us above the mountains, we go up to 14,000 feet. Obviously, we need to breathe oxygen. So the pilot, you plug your mask into the little connector. Passenger will turn the oxygen controller on, and the oxygen will flow quite happily to the mask connections. Charging connection is just there to top the bottle up. Yeah. When the system's not in use, we'll turn it off. Otherwise, we'd lose all the oxygen. Yeah. The regulator that it shows you on the picture on the notes. The regulator is there to bring the cylinder pressure down to breathing level. If we didn't do that, you'd try and put 18,000 psi into people's lungs and they'd be floating away everywhere. Yeah. So your continuous flow provides a steady controlled flow of oxygen to a simple mask, just a cup that fits over your nose and your mouth. Very, very simple, fairly inexpensive, but it does tend to be wasteful. Yeah. Above 10,000 feet, as I've just said, the pilots and the crew are going to breathe oxygen. Continuous flow, we can control that flow by a regulator. The passenger can adjust the oxygen pressure coming out, or the regulator can be automatic. Yeah, the shut-off valve to turn the system on and off. What's the other thing that we can do? We want to conserve oxygen. As we say, once this thing's switched on, the oxygen's just going to flow to the masks. Now, if we want to alter our altitude, we're going to require different amounts of oxygen depending on whereabouts we're flying. So to help us do that, within the system, we can fit little restrictors. Yeah, those restrictors restrict the flow of oxygen to the mask. Yeah, and where the pressure regulator is controlling the pressure to a fixed value, let's say it's pumping out 20 psi constantly, by using these different restrictors, we can adjust the flow of oxygen so it's not wasteful. Unfortunately, you're going to have to remember the color codings for the restrictors. If we've got a restrictor that's color coded red, we're going to use that at lower altitudes, 8,000 to 14,000 feet. It's going to let a lot less oxygen through because we don't actually need it. An orange restrictor is going to get used between 14 and 22,000 feet. Yeah. And that orange restrictor is going to let a bit more oxygen through because that's where we need it. The green, green is used at the higher altitudes, 22 to 25,000 feet. So just to reiterate, these things are continuous flow system. So we've turned it on. The oxygen is going to be flowing continually. It's coming out at steady pressure. Put the little restrictor in the supply line, to the mask, and that will regulate the amount of oxygen that we're giving people. Anybody got any questions on that? That is the regulatory side of things. No, everybody nice and quiet. Everybody happy, I take it then? Anybody actually hear me?
Yes, Jim.
Oh, that's good then. Yeah. You're all alive out there. That's the main thing. Not being deprived and starved of oxygen.
Alive with oxygen system.
Yeah.
Mr. Jim?
Yeah.
Where do we get these colors?
color code?
Yeah, that's what I said. Unfortunately, you'll need to remember that.
Where we find this color code, in where, in cylinder or in max, or where? I don't.
No, it's in the line between the mask and the aircraft connection. Just give me a sec. I think there's a picture of it. Comes up in a couple of minutes. Is that the one? Yeah, I'll come onto a picture of it in a couple of minutes. Okay.
Okay.
Right. Everybody's happy with that then. Yeah. So the oxygen system then, yeah, from our oxygen bottle, yeah, we're going to go through the regulator, and the regulator is going to reduce the pressure to a more usable level. Yeah. From there, as we brought the pressure down, yeah, it says the low pressure distribution pipes, normally made from aluminium alloy. Yeah, gaseous oxygen systems that we're talking about have a manual shut-off valve located in the cabin, operated by the crew. Yeah, and like all things, the valve turns the system off and prevents leakage of the system if the aircraft's parked for a long time. Yeah, got to be ensured that the valve's open before the aircraft takes off. Yeah, got I'll say there. The bottle, open the shut-off valve. Yeah, the pressure regulator, reducing the pressure down to the passenger mask connections. And as it comes off the distribution line, between the distribution line and the mask is where we're going to fit the little orifices for reducing the pressure, or regulating the quantity of oxygen. We'll come on to it later, I think, but just bear in mind that from the storage cylinder, exactly the same as we had with our fire extinguishers, we're going to have an overboard discharge point. Yeah, so within the bottle, there's a little what they call a bursting disc. If the bottle overpressurizes for whatever reason, the bursting disc will rupture and it'll allow the oxygen to vent overboard. Yeah. Where have we gone? There you are. Yeah, the oxygen masks themselves for use with a continuous flow system, they normally use what they call a rebreather bag. Yeah. With that type of mask, the oxygen initially flows into the bag. Yeah. When the person inhales, oxygen's diluted with air and then taken into the lungs. When we breathe out, the air that entered last into the body is still going to contain a large proportion of its oxygen. Yeah. So when we exhale, that sort of air that comes back out of us with good oxygen is mixed in the bag with the oxygen that's flowing, and that prolongs the life of the oxygen that we've got. Me, because I'm handsome. Yeah. When I breathe in, my lungs are going to inflate. So we'll call that a lung. And we'll call that a lung. Yeah, so as I breathe in, the lungs inflate. Yeah, and as the lungs inflate with air, yeah, the top portion of that air, the low portion, the oxygen's absorbed into the bloodstream, and away it goes off to my heart to get pumped around. The top part of the lung, the air isn't absorbed. So as we breathe out, yeah, the used air goes off into the rebreather mask, and that used air, the portion that's got oxygen left in it, what we're going to do is mix that up with the oxygen that's already flowing into the bag and breathe it back in again. And in so doing, we're preserving the amount of oxygen that we can use. Yeah, air that was in the lungs longest, the last to be exhaled, and that air is expelled through holes in the mask. Yeah, so the oxygen, the air in the bag, breathed back in during the next cycle. The masks themselves, disposable masks. Yeah, one use only. So if we have to use the masks, they should get replaced. And to indicate that oxygen is flowing to the mask, we're going to have a flow indicator in the system. Yeah, if oxygen's flowing, we'll have a little green sleeve. If it's not flowing, we'll have a little red sleeve. Yeah. Crew oxygen masks we'll have a look at in a minute. The crew are given extra refinements in their masks. They're going to have a microphone built in there so that they can speak to each other and speak to the ground should the need arise. The masks vary in design, yeah, to make them compatible with the system that they're going to be used with. And the masks quick and easy to fit, fit all the different sizes of face, and easy to disinfect. Yeah, so that is your basic simple mask. The little rebreather bag, yeah, the oxygen supply coming in. Yeah, so as we breathe in, we're taking the oxygen that's coming in through the mask. The initial exhalation, yeah, is going to mix with oxygen that's flowing. The stuff that comes out last is going to get evicted via little valves in the mask. Doom. Yeah. External plastic bag, yeah, the rebreather bag, external plastic bag that inflates every time you exhale. The purpose of the bag to store that exhaled air so it may be mixed with the 100% oxygen. And those things are quite happy and quite effective up to 25,000 feet. Yeah, don't forget we're looking at a small, simple service at the moment. Your supply line, yeah, supply line coming in, and there's a mask connection. Yeah, the mask connection is where we can put our little orifice. Orifice into the supply, or we could put it in the supply line, kind of depends. But we'll say we're going to fit our orifice in here, and that orifice, depending on what colour it is going to provide sufficient oxygen for the flight level we're working at. Yeah. From your mask, you've got your connector there, and as you push your connector into the aircraft side, yeah, that pushes a little valve up against the spring, opens the valve, and now oxygen's allowed to flow. If oxygen is flowing, we'll get a little green indicator. If it's not flowing, that green indicator will turn red. Yeah, so your different types of rebreather bag, yeah, the non-rebreather mask and the rebreather. Yeah, just for mixing. And again, nice and simple, easy enough to fit. Yeah, there. What do I need to say there? Yeah, you probably hear the briefs. Yeah, the bags don't necessarily inflate. Yeah, but so people tend to panic because the bag's not inflating. They think they're not getting oxygen. They are. The oxygen trickle feeds through it, and it's always there in plentiful supply for what we need. Mixes with the air we're exhaling in the rebreather. Excuse me a minute, I've got a parcel coming. You got that? Okay, thank you.
Is it Gorkha beer?
No, I wish it was. It's something for the wife's horse, I think. My wife owns a horse, and it's better looked after than I am. She's always buying stuff for the bloody thing. Honestly, it's got more coats than I have. Has a coat for every day of the year, I think. It doesn't serve any purpose. Yeah, all it does is eat and shit. A bit like children, I suppose. Yeah, just a drain on resources. Yes, our rebreather mask and non-rebreather masks. Yeah, the orifice, yeah, giving us the required amount of oxygen. Rebreather mask has soft plastic reservoir attached at the end, saves 1/3 of the person's exhaled air. Rest of the air goes out via side ports, covered with a one-way valve, a non-return valve to allow that. The non-rebreather, yeah, has several one-way valves in the side ports. Also has a reservoir bag, but the bag only has a one-way valve that prevents the exhaled carbon dioxide from going back into the bag. Do we need to worry about any about that? No, just the fact that there's two types: the breather bag, and the non-rebreather. The cup masks, yeah, the masks that fit to our face, yeah. Simple cup-shaped masks, elasticated head strap, yeah. Put the strap around the back of your head, and sit and breathe normally. If you haven't got a strap, you're going to have to hold the face mask or the mask onto your face. Yeah, it's going to fit all sizes of face. Rebreather bag may be fitted as we discussed. Hoses for the drop-down masks. If you've got a drop-down system, this type, they're held in by a little plastic clip. And that clip will snap when we pull down to pull the mask to our face. Essential part for us as the engineers, when we're stowing these things, make sure that they're stowed correctly, that the pipes are coiled up correctly, so the masks drop down when they're needed to. Yeah. So again, just on page, what page are we on? Page 13 just gives you a nice little picture of the first piece. Yeah, filter in the bottom of it, flow indicator, and the plug that plugs it into the aircraft system. The crew oxygen masks, yeah, they've got to be very, very easily fitted, so that the crew have got to be able to put that mask on with one hand in 5 seconds or less. Yeah, and that includes the fact whether the crew are wearing glasses or not. The quick don masks for the crew, normally suspended in a little access panel next to the crew point. They've got to be able to get in and out of those unimpeded. There shouldn't be anything in the way. Some of them are suspended just above the crew station. The ones I've seen are in little boxes just at the side, so the pilot can just pick it out with his hand, stick it over his face, and away we go. Yeah, they'll take us up to altitudes of up to 40,000 feet. The oxygen masks, as we've said before, contain a microphone, so they've got radio contact. They can speak to each other. They can speak to the ground. Yeah, the mask is going to cover the nose and the mouth, and again held onto the crew's head by a strap. Right, and that's the sort of thing that we're looking at. Yeah, just a little elasticated strap, covers the nose and the mouth, microphone fitted. If anything happens, he can just pluck this out of the air, stick it over his head, and away we go. The newest style of crew masks, yeah, held in a storage box next to the crew station. and they are permanently plugged into the regulator, and the microphone connection is permanently connected. Yeah, so if anything happens, they can just pick the thing up, throw it over their head, and we're away. Yeah, some of the newer aircraft, the harness that goes around the back of the head is actually inflated. Yeah, so as he picks his mask up, the harness slips over the head, the mask goes over the face. Press a button that releases oxygen pressure from inside the harness, and that causes it to get pulled onto his head, pulled on nice and tight. Yeah. So it's just a little button. I don't know whether you got your page open in front of you. Yeah. Shows you a picture of the masks and shows you the little red toggle. So the harness is inflated. As we pull it out, we pull the thing over our head. Yeah. Once that mask's over your nose and mouth, just press a little button or a little lever, and that releases the oxygen from inside the harness, and that now pulls in, contracts, and tightens onto the head of the crew member. The more Gucci masks work on exactly the same principle. They've got the intercom, they've got the oxygen connector, a regulator fitted in there, they've got the microphone, but on these ones there's a face piece as well. So something like smoke in the cockpit, yeah, we've got that eye protection, so the pilot can actually see what he's doing. Yeah, yeah. The storage box, we've got the mask inside. Yeah, permanently plugged in. Yeah, so if the pilot needs to grab the thing, he can do it. He can just pluck it out. As he pulls it out, the harness inflates, slips it over his head, presses a little button, harness deflates, pulls it to his head. Yeah, a flow indicator, just a little doll's eye that's going to tell him that he's got oxygen, tell him he can breathe. And there's a regulator in there as well. We'll go through the workings of the regulator later. But the regulator, all that is doing is just making sure that he's getting the correct amount of oxygen for the situation that he's in. Again, the regulator, I'm duty bound to go through it, but we needn't worry about the internal workings of the regulator. Just example of the mask, the full face mask. It's got the oxygen connection. It's got the comms connection. It's got the full face mask on there and the microphone inside. The little levers to release the pressure from the harness to get it to fit properly. With this type of mask, we can do all our checks at one point. We don't have to be carrying stuff in and out the flight deck. We don't have to pull the mask out the box unless we're checking the harness inflation. All the flow checks and everything can be done at one point, which is quite handy. Yeah, your crew smoke sets provided by the cabin crew. So if we get a smoke-laden environment, if we get a fire in the back cabin and we've got smoke all around, the smoke set just allows the crew to pull a visor over the head, and contained within there, it's a little self-contained oxygen system. Yeah, there is a hose, so the crew, if they run out of the supplied oxygen, they can plug into the main supply. Yeah, the mask got the oxygen feed pipe, got an intercom in there so they can chunter away to each other like they do. As I said, the smoke mask, we can plug it into the ring main system should we need to, and there's a regulator in there as well. Yeah, regulator automatically compensates for changes in altitude so that the smoke set can be used during low cabin pressure emergencies. Yeah, so if we had a rapid decompression, yeah, if the cabin crew wanted to put that on so they can run up and down and serve your your last cup of coffee before you plummet to your death, they can do. So that's the smoke sets. Boom. Oxygen filters, yeah, are normally from the what we call the sintered bronze type, and are provided at various points in the system. Yeah. Some instances, the charging connector is counterboard to house a slug type bronze filter. What happens with that when on the charging system, the charging connection's got a filter inbuilt, but with that filter will restrict the flow of oxygen into the system, so it just makes sure we're not charging it up too quickly. But your sintered bronze, yeah, it's the sintering, if you remember back to module 6, is part of the manufacturing process for our metals. The sintered bronze filter, yeah, just allows the passage of oxygen through, and any contaminants that are in there are going to get trapped. And these things are dotted in the system. Yeah. Anything else I need to say there? No. No. Right. Again, what you see on the slide is very common question. Yeah. Identification of your oxygen cylinders. Gaseous oxygen that we're putting in the aircraft is topped up for externally, and the oxygen is stored in cylinders. The amount of cylinders obviously depends on the total amount of passengers, total amount of crew. Yeah, the crew and the passenger oxygen systems are normally independent of each other. They'll come in from a common charging point, but the crew stuff, they'll have their own storage cylinder and their own equipment. Likewise, the passenger side will be separate. The storage cylinders made from high tensile steel are normally charged to 1800 psi. Yeah, 1800 is the standard oxygen pressure. The size of the bottle depends how much we're carrying. So the storage cylinders from 80 litres up to 2250 litres for large aircraft. Stenciled on the bottle, yeah, will be O2. And depending on what nationality you're running off, depends on the colour of the bottles. Your British oxygen cylinders are black with a white top, yeah, and the words O2 stenciled on the bottle. Also on the bottle, and again worth remembering, is going to be the words oxygen, use no oil or grease. Yeah. Oxygen and oil and grease react extremely violently, so we need to make sure that oil and grease is kept away from all our oxygen equipment. Yeah. But again, just to reiterate and make sure you stick your highlighter through, oxygen cylinders, the British ones, are black with a white top on them. American oxygen cylinders, sorry, are green. Americans always got to be different. Yeah, please, 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 please remember that one. I'm not saying it's a banker, but it comes up very, very often. Yeah, the colour coding for your oxygen cylinders, black and white UK, green American. Additionally, as I've just said, the words oxygen or O2 will be stenciled on the side, and the wording use no oil or grease will be highlighted on there, normally in red. Yeah. Additional information, you might find the manufacturer's name, the drawing number, your test and normal working pressures. We mentioned that before, when it was last tested, and sometimes you'll find the capacity of the bottle on there. Yeah, 80 litres or 120 litres or whatever it might be. But the colour coding, please, please, please remember that. Come on. Anything there? Yeah, no oil. Page 17. Yeah, green, use no oil. What we've got on the bottle themselves, on the cylinders, we're going to have a manually operated shut-off valve to the outlet side. So we've got to open the cylinders before we use them. Yeah, once the cylinders fitted to the aircraft, that valve is opened and it's held in the open position by wire locking, or some means of locking in the open position. Direct reading pressure gauge and a pressure transmitter normally fitted, so that the engineer can see the bottle contents from where he's working, and that information repeated on the flight deck so that the crew know how much oxygen that they've got. The cylinders have an overpressure facility, which is what I was talking about a few minutes ago. That overpressure facility is a bursting disc. It's again a little foil disc within the bottle head. As pressure rises for whatever reason, yeah, whether we've overpressurized it when we're filling it, or whether the temperature outside has increased, yeah, that bursting disc will rupture and it will allow the oxygen contents to escape overboard. Yeah, a green indicator disc blows out when the relief valve has operated, when the bursting disc's operated. Yeah, so this is the skin of the aircraft, very, very similar to the discs we saw yesterday for our fire bottles, but in this case the indicator disc's green. If we get a buildup of pressure in the oxygen system, that overpressure, once it gets to around about 2,800, it says, that overpressure will be felt on the back of an indicator disc. That indicator disc will rupture, yeah, and we'll be able to see that the thing's gone. Normally, the interior of the discharge fitting is painted red. Yeah, so the green disc will blow out. It'll expose a red area, and that should catch your eye fairly swiftly. Yeah, so that's your indicator disc. Yeah, just a little rubber disc. Sits on the aircraft. If we get an overpressure from the bottle, that green disc will rupture, and you'll see the red interior. Alternatively, yeah, to give us an indication that the indicator that the bottle has discharged, the oxygen's released. Some older aircraft, and I was trying to find a picture so I could use it to highlight, rather than having the red interior, what happens is that we've got the bursting disc, but there's streamers inside there, orange streamers. So as the disc ruptures, the streamers drop out. Again, these orange streamers, a bit like silly string sort of thing. So you'd see those streamers dangling down, yeah, and that would immediately get your attention. So you know that the bottle's discharged. Yeah, please do not get your fire bottle and your oxygen indicators mixed up. Your fire bottles, yeah, you've got your yellow piston that pushes out if we've had a deliberate activation. You've got your red disc that blows out if you've got an overpressure. With your oxygen bottles, you've got a green disc that ruptures, and behind the green disc is a red background. Failing that, and you don't see them very often, but failing that, an alternative one, you can get orange streamers. Once that disc has gone, the orange streamers will be released and will flap about. Yeah. So please make sure you don't confuse those little lot. If the
Hello, Jim.
Yeah.
Please repeat that again. For fire, there is a yellow disc which changes into. Please repeat that again.
From yesterday, if you remember back,
yes,
with your fire bottle, if we deliberately discharge that fire bottle, yeah, a little yellow piston is pushed out from the side of the aircraft. So you'll get a yellow indicator protruding from the skin. Yeah?
Okay.
If the fire bottle overpressurizes for whatever reason, yeah, it gets too hot, the pressure inside the bottle will rise to a point, and it will rupture an indicator disc, a red disc on the side of the fuselage. That red indicator disc, yeah, once that's ruptured, we know that there's been an overpressure of the fire bottle.
Okay.
All right. Your oxygen.
In case O2.
In the case of the O2, yeah, which is on page 18 in your books, yeah, you've got a green discharge indicator. When the oxygen pressure gets too high, that relief valve will operate and the indicator disc will blow out. That in turn, the green disc blowing out will expose a red interior of the discharge fitting. So that's your disc. Yeah, this is your aircraft skin. That disc will rupture, and inside here it'll be painted bright red.
Okay.
Yeah, so you'll be able to see that the bottle has discharged. Sometimes, rather than having the red inside, when the disc ruptures, it'll release orange streamers.
Okay, Jim. Okay,
All right.
thank you, Jim. Okay.
That's okay.
Got it, Jim.
Everybody else okay with that? Obviously, if the bottle has overpressurized and the disc's ruptured, we need to know why. So before we replace that, we'll carry out our investigation and find out the fault. 9 times out of 10, it's because whoever's charging the system up has charged it too quickly. The oxygen has heated up as it's going into the bottle, and obviously as it heats up, it raises pressure, and that causes the disc to rupture. Yeah. It says the O-ring in the discharge fitting. If we ever have to replace the indicator, the O-ring's got to be replaced because that prevents moisture getting in. Moisture, same as we've said before, if we get moisture in the system, it'll freeze, and that's going to block things up. Yeah. Pipes in the oxygen system identified with color-coded tape. Yeah, and your color coding, green band with breathing oxygen written on it, and the international symbol is a black rectangle on a white background. Everybody okay with that? Any questions there? There's a couple of nice little pictures in the notes, page 19. Yeah, just showing similar to what I've got on the slide, just the skin, the indicator disc. Yeah, and as that ruptures, the interior of the fitting is a lovely red colour. Older aircraft, as I say, I couldn't even find a picture. It's that old. But because it mentions it in the notes, be aware that alternative to that, you can have a bursting disc, and behind there's little orange streamers that will fall out, and you can see them flapping around in the breeze. If anybody does come across a picture of it, give me a shout. Everybody okay with that? Any questions, queries, anything there? The pressure reducing valves, yeah.
The discs will rupture to red even if the oxygen is intentionally exposed.
No, if you turn the oxygen system on, yeah, the relief valve, that relief valve is there just to prevent overpressure in the bottle. That bursting disc.
So all I mean is the red exposed is just due to the high pressure.
Yeah, yeah. Behind that green disc, this where it says discharge fitting, yeah, inside there is coloured red. So the disc is just a very thin rubber. Yeah. So if you get too much pressure behind it, that rubber will split, and behind there it's painted inside the fitting. It's bright red.
All right.
Yeah, you see in here. Yeah, you've got the disc fitted, but inside that housing's bright red. So if that disc fractures, yeah, if it gives way, you'll be able to see the red inside the housing. You okay with that?
Okay. So can I ask you very quick questions?
Yeah.
So last you have asked which indicator disc will be blown out for a deliberate initiation of an extinguisher. Is it yellow disc?
Yeah, it's two different systems. You've got the fire system, the fire extinguisher, and you've got the oxygen system. It's two different systems, so you've got two different indicators there. Yeah.
Yeah.
This one, the green one, is for the oxygen system. So if the oxygen bottle over pressurizes, let's go back. That's your indicator on the side of the aircraft. Yeah, that's your indicator disc, just a little rubber disc that's held in. This connection is connected to your oxygen system. If the oxygen bottle over pressurizes for whatever reason, it's going to cause that disc to rupture. Yeah, that disc will be blown out. It's only very thin rubber. Yeah, and behind that green disc, there's a red housing, red orifice. So once that green disc is ruptured, you'll see a bright red area behind it. That tells you that the oxygen bottle has discharged because it's been overpressured.
All right.
The fire bottle's totally different system. The fire bottle, you've got two indicators because you can deliberately discharge the fire extinguisher, and you need to know that you've let the fire extinguisher off. Yeah, so there'll be an indicator, that yellow plunger on the side of the fuselage. If the fire bottle overheats for whatever reason, overpressurizes, yeah, then it will vent overboard. Venting overboard, it'll rupture the red indicator disc. Yeah, so it's two different systems. Okay.
All right.
Lovely. Okay. Right. The pressure reducing valves in the system, yeah, reduce the high pressure oxygen from the cylinders down to the lower pressure that we need for feeding to the people. Yeah, so there's the high pressure side and the low pressure side, and the pressure reducing valve is just there to bring that pressure down. Yeah. Pressure is reduced from 1800 psi down to about 80 to 100 psi, roughly. If you try to put 1800 psi into a person, yeah, if he was breathing in that sort of pressure, you'd do yourself an awful lot of harm. So we need to bring the pressure down to a usable level for breathing in and out. Yeah, so that's your reducing valve. The ring main, yeah, is just the distribution for the oxygen. Oxygen system, we've got the storage cylinders, yeah, and we top up those storage cylinders from an external charging panel. From there into the cabin, then that's where we've got our on-off valve. Through the on-off valve, and the oxygen is going to be distributed around a ring main, and at various points you've got your PSUs where the oxygen masks are going to be stored. Okay with that? That's your distribution ring main. Again, page 21, just a nice little picture just to show you where the bottles are held. Yeah, bottles stored, topped up externally. Then there's a feed pipe off to the on-off switch, and then from the on-off switch, you're going to go to the passengers. Ta-da! Yeah, that oxygen then, once it's selected on, is going to be flowing up to the PSUs. Now the PSUs are the passenger service units, and the passenger service unit's got a little door that drops down, and behind that little door you've got your oxygen masks. One mask for each passenger, yeah, in the seats that the PSU is above. If we get a low pressure depressurization, that door will open automatically and the masks will drop down. As the masks drop down, the passenger grabs hold of it, he pulls on the mask, and it's the action of pulling on the mask that allows the oxygen to start flowing. What they don't tell you, in the PSU door, is that the crew have got a switch whereby they can deliberately drop the masks if we need to. So if the automatic system isn't working, there's the backup in the cabin, and the pilot, if he decides that the passengers need oxygen, rather than the automatic system working, again he can deploy it. The two types of system, the gaseous system, where we come off the ring main. The other type of oxygen system we'll talk about in a minute is the chemical generator, and that's a little self-contained unit that when we pull the mask, we pull the pipe, that starts off a chain reaction which starts producing oxygen. We'll come on to those in just a moment. Right, so our pneumatic oxygen supply, we're going to use part of that oxygen supply to open the doors for us. Yeah. So what we have is oxygen introduced into the door mechanism. Yeah. As the oxygen's introduced, it's going to push on a little piston. That piston will push on a latch plunger. The latch holding the PSU door. As the latch opens, the door's going to drop down. Yeah. At the same time, the oxygen flowing through is going to be sitting waiting at the mask supply. As soon as the passenger pulls down on the lanyard that's holding the oxygen hose, it pulls down that allows the oxygen then to open the little valve, flow valve, and that starts the oxygen flowing. Yeah, so pneumatic door, small pneumatic plunger fitted above each of the doors. Doors held closed by a spring-loaded latch. Oxygen made available to passengers. The pressure is used to extend the plunger. That overcomes the latch spring. The latch is withdrawn and the door now just falls down. The masks then fall out. Yeah. If they need oxygen, the user pulls on the mask as he's pulling it down, sharp tug, and that pulls that flow control pin back, and that now allows oxygen to flow through to the mask. Yeah. Should we need to stop the flow for whatever reason, there's a little closing toggle switch, just that little on-off switch there. Yeah, if they want to close it off, they can turn that, and that will reset the wee valve and stop the oxygen flow. Yeah, each PSU oxygen supply has got to be stopped by that method individually, and should this one always gets me. Should the PSU door fail to open automatically, a thin item such as a plastic card can be used to push a red painted manual actuation pin which will withdraw the latch. Again, that manual actuation pin, you get a card or a pen or whatever, you push it up against a wee spring. That's going to allow the latch to open, and that's going to allow the door to drop. Yeah, that's something that's never mentioned in the brief for obvious reasons. But if you're ever in that horrible situation where the masks have dropped and you haven't got one, yeah, just try shoving a pen or a card up the side of the door, and hopefully it'll open the door for you. Oxygen pressure to the masks needs to be reduced to about 10 psi. 10 psi isn't sufficient to open the doors, so there's a double regulator that's used. The initial surge of oxygen is high enough, the pressure's high enough to open the doors. That high pressure is then reduced to breathing level to about your 10 psi. Continuous flow from the oxygen system because it's switched on. Yeah, and away we go and carry on breathing. Yeah. Additionally, the PSU, pneumatic flow regulator, will initiate the flow of oxygen at high cabin altitude, above 14,000 feet. Yeah, cabin altitude. The masks will automatically deploy. Remember, we said earlier in the pressurization section that at 10,000 feet we'll get a warning light. Yeah, that's to let the pilot know that the cabin altitude has reached 10,000 feet. If he ignores it or for whatever reason doesn't pay any attention, if that cabin altitude goes up to 14,000 feet, then the oxygen will automatically deploy. Yeah. So it'll deploy high cabin pressure altitude. It'll deploy manually if we press it manually, or if the pilot makes a selection. Yeah, it'll automatically do that changeover from that initial high pressure that's going to release the door to a breathing level of 10 psi. The crew will get a warning now, or an indication, I should say, not a warning. They'll get an indication that the passengers are receiving oxygen, and it says that the regulator itself is set up so that at higher altitudes it's going to regulate the amount of oxygen that we're giving to the passengers. I'll just run through this. Yeah, it's just exactly what we've said. You've got your oxygen supply coming in, plunger, little latch, yeah, the manual pin. That's your PSU door, the lanyard pin, and the wee leaf spring. Yeah, set off your oxygen. Yeah, the pressure hits the plunger. Plunger releases the door. Yeah, the door drops down during gravity. Yeah, the lanyard's pulled. Pulling the lanyard opens the leaf spring, and that allows the oxygen to flow to the mask. Toggle lever we've already mentioned, so we can switch the oxygen off if we so desire. With the chemical generators, we haven't got that gas there to open the doors, so we're going to use a little electrical solenoid to do that for us. Yeah, so where we've got chemical generators, PSU doors again held by a latch, but in emergency the latches are released by a solenoid. Solenoid operates as striker, and the door opens under gravity again. 14,000 feet, those doors can be automatically opened again by a little aneroid switch in the system, or alternatively the pilot can select them for us once we get to 14,000 feet. Yeah. All it is with these, yeah, we're just going to podge a button. By podging a button, the solenoid is going to energize. Yeah, solenoid energizes, it pushes that plunger forward, which unlatches the door. All okay with that? Yeah. Because we haven't got the oxygen supply there. The oxygen's coming from a generator, not from the main system. Yeah, the solenoid will push the plunger out, door will drop, mask will drop, and the passenger can again pull on the lanyard, and that's going to open the oxygen feed down to the mask. Yeah. Flow regulator, we've talked about that. Yeah. Cabin altitude, manual actuation, switching the cabin. Yeah, it's going to give that changeover of oxygen pressure, give indication to the crew that passengers are getting oxygen, and compensate for different altitudes. Electrically operated system, as I said, our oxygen is contained in a little self-contained generator. A chemical reaction releases the oxygen. Yeah, so to get that, what's going to happen is a button is going to be pressed, or a signal is going to be sent to a solenoid. That solenoid is energized. I think it's something like 5 seconds. Haha, yeah. Yeah, page 25, very top line, page 25. Usually incorporate a time delay of about 5 seconds into the solenoid circuit to remove power once the PSUs have dropped. And the reason for that, it just prevents overheating of those solenoids. Yeah. So the 5 second timer on the solenoid, press the button. Yeah. And again, the thing will drop quite happily. The masks will drop down. Tug on the mask, and away we go. And that, guys, is a good place to stop and have a cup of tea before we move on to what's happening with the provision of that oxygen. So unless anybody's got any questions, 15:35, 14:45. So we'll have a 10-minute break there, and then we'll regroup and finish it all off. Anybody got any questions then?
After tea.
After tea. Okay, then. I'll see you back in 10 minutes then. Unless you want a bit longer, do you?
No.
No? Okay, 10 minutes. Okie dokie, picking a pokey. Right. Let's finish this little lot off. Before I start on the next bit, has anybody got any questions from the first section? First bit that we covered? No? Okay, fine. Right. Flight crew oxygen then. Yeah, we need to ensure that the crew are provided with oxygen, and the system that they use is what they call the diluter demand system. Yeah, that allows the crew members to grab oxygen anytime that they want during the flight. With the diluter demand system, the oxygen's mixed with air, and that mixture is supplied when the user is breathing in, when he's inhaling. What we've got is the high pressure oxygen cylinder, a reducing regulator that we talked about, the shut-off valve we talked about, distribution lines, and the diluter demand regulators. Oxygen mask connected to the diluter demand regulator at the crew station. Yes, he's got his mask. He pulls that out, yeah, grabs the switches, sticks that over his head, and the diluter demand regulator is now ready to feed him oxygen air mix, pure oxygen, or forced oxygen. It depends what he's desperate for. Again, the system from the bottles has got the discharge indicator. It's in a common line. And away we go. Let's see if we can sort that one. Yeah. So our diluter demand system, yeah, we've got the cylinder with the shut-off valve on, the discharge indicator, and the safety disc we call the rupture disc, the blowout disc. Yeah, that just means if the bottle over pressurizes, that the contents of the bottle are going to be dumped overboard. The discharge indicator will rupture, allow that pressure out, and either your orange streamers, very unlikely, or a red interior to the indicator housing tells us that the bottle's discharged. We've got a cylinder pressure gauge, so we know what pressure we've got in there. We've got the ground charging facility, system shut-off valve, down to the pressure regulator valve. Yeah, and from there, we've reduced the pressure to a usable level. Yeah, and then we'll go down to the crew mask connection points. Yeah, there'll be a tapping off. No, there won't. Yeah, off down to the crew points. Yeah, the diluter demand regulator. Yeah, 3-position switch. Got an indicator in there to tell us that we've got oxygen flow. Yeah, we've got a normal selection, which is your air oxygen mist. We can get 100% oxygen. Yeah, and then there's an emergency facility. I'll come on to that. But basically, the emergency facility is forcing oxygen into the user's lungs. Yeah, you've got the picture on page 26, which is happy days. Yeah. Again, nice picture. Taken straight from the notes. Yeah, regulators used in crew oxygen systems designed to adjust the output ratio of oxygen and air in accordance with the cabin pressure and to supply on demand the correct air oxygen mixture. Yeah, typical system. We've got an on-off switch. Yeah, in the off position, the oxygen's just held in the closed position. Yeah, turn the system on. We're now going to let oxygen into the regulator, and to signify that we've got that flow, we've got a flow indicator in the line. Yeah, flow indicator telling us that oxygen's flowing. Yeah. Diluted oxygen in accordance with cabin altitude be supplied to the crew member's mask when the user inhales. What we've got, if we're in the normal position, yeah, there's an opening to the cabin, yeah, and that's allowing cabin air into the regulator. As the user inhales, yeah, the little valve's going to open, yeah, and that's going to allow oxygen to flow in, mix with the air, and off to the crew member's mask. Yeah, the amount of air mixed with the oxygen controlled by the regulator, and the air decreases as altitude increases. Yeah, the amount of air that we're feeding in is decreasing until we're going to get to the point where he's breathing 100% oxygen. Yeah, that's altitude dependent. If he selects 100% oxygen for whatever reason, yeah, flicks the switch up, the inlet to the cabin air is sealed off, and every time he breathes in, valve's going to open, yeah, and oxygen is going to flow through. Yeah. So now, as we flick the switch, we're opening that oxygen. Yeah, when he breathes, he's just going to take oxygen straight to his mask. In the emergency position, yeah, we've got the emergency lever. What happens, he flicks emergency, that valve is then forced into and held in the open position. So rather than working on the inhale, exhale of the user, of the lungs, yeah, that is now held in the open position, and there is going to be a positive feed of oxygen right the way through to the mask. So if he's breathing in, that oxygen is going to be forced into his lungs. As he breathes out, he's really got to make the effort to exhale. Yeah, so that there's always going to be oxygen there. The test button on there, there's a test button somewhere. Yeah, test mask selected, oxygen supplied at high pressure, then provided for the emergency condition, and we can use that for testing the mask. And making sure that there's no leaks or anything there. So that's the diluter demand system. The diluter demand just mixing the oxygen with air, and it works on his breathing pattern. If he goes into the emergency situation, that oxygen is going to be there at his lungs. Yeah, don't forget that prescription, please. Excuse me 1 minute. You remember that script? Sorry about that. Right, yes. Here we go. Just again, more for the ab initios. You're on/off lever. Yeah. Depending on the altitude, the aneroid capsule will position the metering valve. Remember, we said the higher we go, yeah, so that the aneroid capsule is closing off, metering the amount of oxygen in. Depending on altitude. Lower altitudes, you don't need as much oxygen. Higher altitudes, it'll back off. Turn the thing on. Yeah, oxygen up to the demand valve. User inhales. Oxygen flows up to the mask. Yeah, and don't forget we've got our indicator there. Stop inhaling. The valve will close. Yeah, go to 100%. You're shutting off the cabin feed. Yeah, inhale, 100% oxygen supplied. Yeah, and go to emergency. As we said, there's continuous flow of oxygen at the mask. The pressure demand regulator, yeah, as it says there, provides oxygen under positive pressure all the time. Positive pressure, forceful oxygen flow slightly overinflates the lungs, pressurizes the lungs to a lower altitude, allows you to fly at higher altitudes, where 100% oxygen without that that higher pressure will not do. Yeah, so your pressure demand or your diluter demand, the pressure demand doesn't have that mix of air coming in with it. The air's not diluting the oxygen. The pressure demand is there and putting that oxygen through to the user at positive pressure. Anything else we need to know on that? No. Just gives you an idea of how to do the checks. However, stipulation there, always follow the AMM. Wunderbar, wunderschön. Your chemical oxygen generators then, yeah? These are little self-contained generators, yeah? And they contain, they're made from corrosion-resistant steel, allegedly. They contain an insulating liner because the chemical reaction that is caused by the generators generates an enormous amount of heat. So we need the insulation to keep the heat in. Yeah. Inside the insulating liner, there's a block of sodium chlorate and iron powder. Filter surrounds the sodium chlorate. Firing mechanism operate by a little lanyard. Let's just rewind on that first. The advantages, just so you know, yeah, we don't need all the storage cylinders, the pipes, the regulators in a conventional system. Very, very reliable, and because you've got one generator per passenger or per person, each one, if you had one generator fail, it's not going to affect anything else. Nobody else is going to suffer. Very little maintenance required. Yeah, the generators will get replaced every once in a while. We don't need to replenish them. Yeah, if they do get used, we just replace them. So it's a really easy little system. Like I said, you've got this insulation surrounding a block of sodium chlorate. Sorry. Yeah, and in there is we said iron as well, iron powder. Yeah, the generator has a little firing mechanism. Yeah, and the firing mechanism is operated by a lanyard that's attached to the mask. So when we pull the lanyard, we are operating the firing mechanism. Yeah, as that fires off, yeah, chemical reaction starts to take place between the iron and the sodium chlorate. And that chemical reaction is going to generate oxygen. Yeah, low pressure oxygen flows through a filter and onto the outlets to the mask. Yeah, so off we go. 3 masks, 3 outlets. The little generator. Yeah, and that's chugging away, providing our oxygen for us. Yeah, so it flows through the filter, off to where it needs to be. That oxygen flow will last for around about 15 minutes. So that the general accepted figure is a 15-minute of supply of oxygen from the generator. Page 29, run a highlighter through 15 minutes. Yeah. The temperature produced at the generator is very high, but the oxygen that's being delivered to the mask is well within limits, 10 degrees. A lot of oxygen provided. As I say, it'll give us 15 minutes, which should be enough time to get us down to a breathable level, yeah, for our oxygen. Temperature sensitive tape, normally wrapped around the outside of the cylinder, and that's an indication as if the oxygen's or the generator's been fired, generator's been used. Normally provides about 10 psi, so we don't need regulators with the thing, so that's another weight saving. And just on the end there, just to mention, there's a little relief valve. So if for whatever reason, very, very unlikely, but for any reason, pressure builds up, the relief valve will operate and vent the oxygen off. Yeah, that was the advantages that we've talked through. Right. Page 31. Yeah, page 31. I'm going to go through that, read it out. If a serviceable oxygenator has been removed, before we remove it, we've got to fit a safety pin. That safety pin prevents the firing mechanism from activating. On the fitment of the generator, the safety pin's got to be left in position until the generator is fully secured in its clamps. Yeah, once everything's in, yeah, firing pin's installed, lanyards are slack in the final position, then the safety pin can be taken out. So the last thing that gets removed is the safety pin. The safety pins have a warning pennant attached to them to prevent them being left fitted. Under that sentence, yeah, highlighter. Gaseous oxygen generators which are time expired or which have been used must not be transported by air. I repeat, gaseous oxygen generators which are time expired or which have been used must not be transported by air. New or unused generators intended for air transport must be prepared for carriage in accordance with dangerous goods by air regulations. They are not to be carried in passenger aircraft. Yeah, that is well worth remembering. That comes up quite frequently. Those are your cylinders, yeah, your safety pin, the safety pin with the lanyard fitted, the heat sensitive tape on the things to let us know whether they've been activated or not, your discharge outlet that's going to screw into the oxygen system. This was the result, or in fact, the one I'm thinking of was even worse. But there have been a couple of incidents, of which this was one, where oxygen generators had not been prepared properly, had been transported and had led to aircraft fire. The one I'm thinking of it was a value jet aeroplane, and that crashed in the Everglades in Florida. And what had happened, the company, there'd been a load of generators, old generators removed from an aircraft, had to go back to the manufacturer for overhaul. They all got thrown in a box, no packing around them or anything, thrown in a box into a cargo aircraft. Along with the generators, there was lots of other cargo. There was a couple of wheels in there, and so on and so forth. Anyhow, aircraft took off. Because the generators hadn't been secured, they were bouncing around, and one of them fired, went off. And the heat that was generated caused the other oxygen generators to fire. And of course, that's a really oxygen-rich atmosphere now in a cargo compartment, nowhere but nothing but for the fire to carry on raging. Yeah, it was constantly being fed by oxygen. Then you had the tyres that were in there. They melted, they exploded. The exploding tyres went through all the control cables. The aircraft just nosedived into the Everglades. Really, really nasty and totally avoidable. which is why now we have such stringent regulations with oxygen generators. So please, please, please make a note of that. Yeah, time expired or used generators must not be transported by air. New, unused generators intended for air transport must be prepared in accordance with dangerous goods regulations, but they are not to be carried on passenger aircraft. Once the generator is fitted in an aircraft, yeah, in its correct location, then there ain't a problem, but transporting them, it can be. And then there's a warning, just reiterating what I was saying, that these things are dangerous and they need to be handled properly. Anything else that we need to worry there? No. Yeah. Dangerous air cargo, dangerous goods. Therapeutic oxygen. Yeah, we said that we need to be able to provide therapeutic oxygen for 2 passengers or 2% of the passengers, wherever they're located in the aircraft, whatever the greater number was going to be. So what your therapeutic oxygen is emergency first aid oxygen, normally carried around in little bottles, yeah, and the stowage for those bottles should be highlighted by placards and all the other good stuff. Yeah, self-contained. Yeah, the self-contained bottle got its own on-off switch, got its own little regulator on it, got its own little contents gauge. They've got 2 outlets to which we could attach masks. Yeah, cylinders normally charged to 1800 psi, and for your therapeutic oxygen, yeah, we're looking at 120 litre capacity. 120 litres for your therapeutics. Yeah, the cylinders normally come in a little bag, but they've got a carrying strap, so we can get to where we need to be. The 2 outlets are high flow and low flow outlets. Yeah, so as you see on there, we've got high flow, we've got low flow. The low flow outlet will deliver 2 litres a minute and give 60 minutes duration from that 120 litre cylinder. The high flow will give you 4 litres a minute and obviously 30 minutes duration from the cylinder. Yeah, the outlets, fluorescent labels sometimes attached to the high flow for easy recognition. The ones I've come across, it actually tells you high flow and low flow. Yeah, so there's no dicking about. If 2 masks are used, yeah, hoses available, 2 passengers can use the same bottle at once, one on the high, one on the low. Yeah. Oxygen pressure in each cylinder checked for correct pressure on each daily inspection of the aircraft. If the cylinder is used for any reason, cabin crew should make a note in the tech log or the cabin log, and those cylinders need to be replaced or replenished before flight, and the masks would need to be replaced. Yeah, so those are examples of your therapeutic oxygen bottles. Has anybody seen the film Airplane? Yeah. Right. If you've got a sense of humour, yeah, and although it's American, it's ever so funny. Really, really good film to watch. Is Airplane. Yeah, that's a clip taken from it. Young lass on her therapeutics there. Honestly, seriously, if you've not seen it and you get the chance, yeah, watch Airplane. It's funny as anything. Really, really funny. In fact, there's that much going on, you probably have to watch it twice so you see all the jokes. Strongly recommended. Sorry?
After exam.
After the exam, yes. Yeah, no, just at some point in your life, yeah, watch Airplane. It really is funny. Watch it before the exam, help you relax.
And help us to fail.
You're not going to fail. Stop that. You're not going to fail.
To have even no times for eating and for lunch also. How can we enjoy, sir? It's very
Sorry?
difficult for us.
Can't hear
We have
you.
no time. We have no time for lunch and breaks also because having a very busy schedules.
No time.
Yeah.
Do you know when the exam is yet? Has anybody said when the exam is?
When? When
Yeah,
is the exam?
I'm asking. I don't know. I don't know.
Hopefully 2 weeks after the completion of the course.
Okay. Yeah. Normally they leave a gap for you guys because you like to. You need that time for revision because a lot of you are working.
Yes.
Yeah, I know that's happened in the past where there's a gap between finishing the module and doing the exam.
This time we expect more gap because we have long online classes. In the morning we join the duty. From the duty we rush to our home and quickly turn the computers, stay in the computer for 7-8 hours and go to sleep, and again the same.
Same.
Schedule.
Yeah.
So
Yeah.
once we go in the class, we don't have even a time to turn the book. Only in the weekend, one day.
Yeah.
Definitely.
Actually, when we used to come out teaching, we used to do this, but in a lot quicker time. So we'd come out, and in fact, the last time I was out there, which was just about a year ago, or just over a year ago, we'd start at 5 in the morning. Yeah. The guys would come in, would start at 5 in the morning, would finish about lunchtime, and then they'd go off and do the day's work. Then go home, revise, go to bed, and the same thing would happen again. But we did module 11. I think we're doing it in about 3.5 weeks. When we were teaching face to face, we were doing a shorter time. We're doing sort of 4-hour days, but we had even less time to do it. So we've had a little bit more time online just to make sure that the understanding and everything's going across. Online teaching, I totally agree with you. It's not the best, but in this day and age, what can you do? Yeah, it's
Yes,
we can't travel, so we've got to come and.
We have only this option in hand, so we have to utilize.
Yeah. It's strange way of having to do it. So when you're sitting in the classroom, when you're face to face, you can answer questions there and then, and you can see whether people are understanding what you're saying. You can see how they're feeling. You can gauge everything, but you can't do that on a computer. It's a lot more relying on people talking to each other, and we seem to have been managing that. Yeah, and
Yes.
the questions that are coming back and the understanding that's being checked, it's making me confident that you guys are putting the effort in and that you know what you're talking about. Yeah. So, at the moment, it's looking quite good from my point of view. I've got the confidence in you guys that you'll do all right in this. At the moment. Yeah, you just need to have that confidence in yourselves. Yeah, you need to reassure yourself that you can do it, and you know it. And you work on aircraft. Yeah, you can draw on your general experience of aircraft. We're not looking for anything type specific. We're looking for generic stuff. So oxygen systems, we're just talking about oxygen systems that are fitted on basic aircraft. We're not looking at A320 or 737 specific. Yeah, we're just generalizing. So as I said before, even if you don't know, with your experience, you know, you've got a good background knowledge to help you, an understanding to help you with any struggling questions. But anyhow, meanwhile, back at airplane, yeah. If you ever get 10 minutes, have a watch. It's really funny. Therapeutic oxygen, which you're all going to need. Yeah, we're going to provide to the passengers, as we say, portable bottles. 1800 psi. They've got a regulator fitted to the bottle, which will reduce that 1800 down to usable level. The bottle's 120 litre capacity, stored in easily identifiable locations. The bottles themselves, the two outlets, the low flow and the high flow. Remember low flow, remember high flow, whatever page that's on now. 33, yeah. So low flow, 2 litres a minute, an hour's duration. High flow, 4 litres a minute, 30 minutes duration. Obviously, if the bottle's used, it's got to be replenished before the next flight, and any masks that have been used need to be replaced. It does say that there's a requirement that all portable oxygen equipment carried on the aircraft have got to be provided with an over-temperature or an overpressure relief device. That pressure relief device is normally incorporated in the bottle, but it does say that if failure of the part of the bottle, so if let's say the contents gauge melts, it's going to let all the contents out. Yeah, so we're not going to have an overpressure. There'll be a pressure relief facility in there. Most of them have got a little pressure relief valve incorporated, but the regulations say that if something like the gauge melts or another component fails, and that can provide the same function, that's fine. Fusible plugs, yeah, could use them. So your therapeutic bottle, yeah, charge it up, 1800 psi. You've got your on-off valve. You've got your two connections, your high flow, your low flow. Relief valve in the system. Yeah, the fusible plug is just there if it's in a fire or whatever. The high temperature, the fusible plug will melt. Not a lot else to say about that. Yeah, and the pressure regulator just reducing the pressure from the bottle to a usable level. Controls indication for our oxygen system. Yeah, indications, pressure transducer in the cylinder. It's going to send off a pressure reading to the gauge in the cabin, and a pressure sensor in the manifold indicates manifold pressure. Passenger and crew storage cylinder pressures are shown in the cabin by your electric gauges. Yeah, and adjacent to the pressure indicators is a light to show that we've got the passenger system switched on. Yeah, the passenger system has deployed. Yeah, the automatic operation, or if the crew want to select passenger oxygen, they've got that on-off switch for that. Yeah, so your oxygen pressure gauges, crew oxygen, passenger oxygen. The passenger oxygen, normal, automatic, or on, so we can select that. That initiates your oxygen flow, obviously, and then the light, the indicator to tell you that the passengers have got oxygen. Yeah, again, just examples of the different different panels. Yeah, passenger oxygen on, the crew oxygen. Yeah, plenty of pressure in there. Passenger oxygen, normal selected. Yeah, it's a guarded switch. When we say guarded, so again, it's a conscious decision to make that selection, and an indicator tell you it's flowing. On this one, it's actually telling you how much oxygen you've got, what size cylinder it is. Boom. All right, there is somewhere. Bear with me, bear with me, bear with me. Not that one. Right on page. Yeah, I'm just trying to find it. It's in there somewhere. But please just remember, while we're talking about the indications, if the aircraft cabin altitude gets to 10,000 feet, a warning light will go on in the cabin. If the cabin pressure then gets to 14,000 feet, cabin altitude, then the oxygen will automatically deploy. The ICAS indications, yeah, we needn't worry about. It's just telling us what indications that we're going to get and where they're going to come from. The fact that it's on the ICAS is neither here nor there. Yeah, what could cause those messages? Don't worry about that. Passenger. Oh, here we go. Here we go.
Excuse me, Jim.
Yeah.
Please just this mention that last you have.
I'm just looking for it. I'm trying to find it. But when we talked about the pressurization, we said that we're going to get the warning light coming on at 10,000 feet to say that the cabin altitude is at 10,000 feet. At 14,000 feet, and that we went through that a few pages ago. At 14,000 feet, the oxygen will automatically deploy. 14,000 feet cabin altitude. Okay with that? Happy days, happy days, happy days, happy days. Right, I'm just going through the stuff on page 40 onwards. I just want to make sure that I've covered everything, that there's nothing that I've missed for you guys. Yeah. Your crew oxygen, yeah. Crew system supplies each crew member with oxygen. Crew masks receive oxygen from a pressurized cylinder. Each mask has controls for adjustment by each crew member. Has somebody got the microphone on?
सुरेश सर अफ गर्नु न माइक हजुरको फिडब्याक आइरहेछ.
Okay. Yeah, so your crew, yeah, they've got their bottle, yeah, their cylinder. That cylinder feeds up via a regulator and a demand regulator. Allows oxygen to flow to the crew mask. The diluter demand, yeah, mixes the oxygen with air, and it adjusts automatically for altitude. Yeah, so the crew mask from his bottle, yeah, switches on, goes through a regulator, and then to the crew masks where they've got the diluter demand regulators, and There we go. Remember, we said that it's going to cover the nose and the mouth, and they'll have a radio microphone facility built within their mask. The diluted demand mask for them. The oxygen cylinder. What we need to say about cylinders, don't forget the colouring for the cylinders. Black and white for UK, green for American. Yeah. And it will have no oil or use no oil or grease stenciled on the side. Yeah. The cylinder itself has a shut-off valve, so we can close off the supply when we're replacing the cylinder, changing it over, and it's going to have a charging facility, so we can charge it in situ. We can charge the cylinder up. If that cylinder becomes over-pressurized for whatever reason, yeah, we've got what they call a bursting disc in it. The bursting disc will activate, and that will send bursting disc goes, and that will send all the oxygen overboard. As the oxygen goes overboard, it's going to rupture the indicator disc, and the contrasting colour behind the green disc, the red colour internally, is going to highlight the fact that the bottle has discharged. Yeah, if the bottle has discharged, then we need to investigate why before we replace the disc. As it says, side of the aircraft, skin of the aircraft, when we're doing our checks, we can see that quite easily. The fill panel, or the servicing panel, yeah, is where we're going to fill the system up from. Allows the crew oxygen cylinder to be filled without removing it from the aeroplane. Yada yada. The masks for the crew, kept in storage boxes at each crew station. Yeah, as he removes the mask, the harness is inflated with oxygen. As he slips it over his head, flicks a little button, that releases the oxygen in the harness and pulls it onto his head. Regulator just reduces cylinder pressure down to usable pressure. And then it goes through a description of what's going on. Nothing we need to worry about there on the notes. Yeah, that was dealing with the crew side of things. And it's giving you a typical example from a 767 crew oxygen. Right. Yeah, so got your masks. Got your bottle, yeah, no oil or grease. Along with that, we're going to carry therapeutic oxygen. Therapeutic oxygen, your two outlets, your low flow and your high flow. 4 litres a minute, high flow, 30 minutes duration, 2 litres a minute, and 60 minutes duration for the low flow. The masks that are provided, yeah, depending on the type of system we've got for your large aircraft, they're going to deploy from the PSUs above the seats. As the mask deploys, pneumatically or electrically, I should say, the mask will fall. As we tug on the mask, that is going to initiate the flow of oxygen from whichever system, gaseous or the chemical generator. Chemical generator has the electric release, the solenoid, and that solenoid is only energized for 5 seconds. That prevents it from overheating. The pneumatic release uses an initial surge of oxygen to release the door, and then that oxygen pressure is reduced as the oxygen's fed to the passengers. Your standard breather, non-rebreather bags, yeah, just allow oxygen to flow through into the user. The rebreather bag, we're mixing oxygen from the lungs with the oxygen coming from the supply system, mixing it together and re-inhaling it, and it just conserves the amount of oxygen we're using. Another method of conserving oxygen as well is those little orifices, the colour-coded orifices. and depending on the altitude that we're operating the aeroplane, depends on what colour orifice we're going to use. Red, below 10,000 feet, I think it was. Amber, 10,000 to, was it 14,000 feet? And green, above 14,000 feet. I can't remember the exact figures off the top of my head.
Red is 8 to 14, and orange is 14 to 22, and last one green is 22 to 25, I think.
Okay, thank you.
Well,
yeah, I couldn't remember the figures off the top of my head. Anything else we need to say? No. Your pipelines, your regulators, we've covered those. The mass connections, the orifices, flow indicator, just a little ball that's in the line that's going to tell us that the oxygen's, or ball or a sleeve that's telling us the oxygen's flowing. The regulations, don't forget the minimum sector altitude. Depending on where we're flying, depends on the amount of oxygen equipment that we're carrying and whether we can get down to flight level 120 before within 5 minutes. Working on the system, any oxygen system, we did say it reacts really, really violently, explosively with oil and grease. So oil and grease must be kept away from any oxygen equipment, hoses, fittings, all that. If you're working with oxygen, don't have filthy overalls on, don't wear greasy overalls, and don't have crap all over your hands. Yeah, it really does react badly. There's a famous story when I was in the Air Force, and the pilots used to have huge, big mustaches. It was their thing, big, what they called handlebar mustaches. And a particular aircraft we had called the Canberra used to go off and do reconnaissance missions, and it was airborne for sort of 7 or 8 hours at a time. Because it was up for that long, the crew used to be given a box of sandwiches and crisps and a carton of juice to keep them going. And this particular day, the pilot had been flying. He'd opened up and they'd given him cheese sandwiches for his lunch. So he ate his cheese sandwiches. Fantastic, not a problem. About 10 minutes after that, they had a pressurization problem. So they had to put oxygen on. So the pilot put his oxygen mask on, turned the oxygen on, and that oxygen reacted with the grease from the cheese in his sandwich that was trapped in his mustache, and it burnt his face. Yeah, it was not in a bad way, but it was a nasty burn that he got. And that's just an example of how volatile oxygen and grease can be. Yeah, so keep oil and grease away from any oxygen equipment. Also, keep oxygen away from fire. Yeah, oxygen really promotes combustion. So if you've got a fire in an oxygen-enriched atmosphere, woomph. No smoking anywhere near the oxygen equipment. Handle components carefully. Yeah, the oxygen cylinders, are quite fragile. Yeah, if they're mishandled, and if they go, it's going to go explosively. Yeah, especially the fittings on the end. If that fitting, the end cap, snaps off for whatever reason, the rest of the cylinder is going to go off like a torpedo. Yeah, it'll fly down whichever direction it's pointed. So make sure you handle the equipment properly. The other thing that's quite important is the oxygen that we use for breathing. Yeah, is designated as aviation breathing oxygen. It is a lot more pure than other oxygens. Yeah, welding oxygen, medical oxygen, they contain moisture. Moisture would freeze at altitude and prevent the system from working. So only use aviation standard oxygen in the systems. Yeah, and your equipment should be marked up as such. Anything else I need to say? No. Handle stuff carefully, don't mix. When you're charging your oxygen equipment, always charge slowly. If we're charging and we charge too quickly, we're going to get a rapid buildup of heat. That rapid buildup of heat is going to increase the pressure, and the chances are the bursting disc will fire, and then you're into a whole world of pain. Other things when we're charging systems, no refueling operations taking place at the time, no fiddling with electrical switches. There should be signs put around saying that oxygen charging is being carried out. Make sure all our bonding and earthing has been done properly, and that the correct firefighting equipment's available around us. Oxygen equipment will be marked up as oxygen. Yeah, your black cylinders, your white cap, again clearly marked up as oxygen. Only use that specific equipment. It used to be, and I don't know whether it still applies, but it used to be that the oxygen hoses used to have a left-hand thread, so you couldn't put oxygen into the wrong system. But I genuinely don't know if that's still the case. Yeah, your oxygen charging point. Yeah, well, we're going to connect in, top up, and we can read what the contents of the bottle is as we're doing it. As I said, we've got to charge slowly. We don't want that heat build up. Sometimes you can get special connectors that you use in the system that act as a heat sink. Yeah, the thermal compensator. It's got a little sort of wire brush inside it. And the little copper wire brush just dissipates any heat that might be building up. I think it mentions them in here. Where are you? Yeah. Prevent excessive temperatures being built up in the pipelines from the charging point of the cylinders. Thermal compensators are installed. The compensator acts as a heat sink to disperse any buildup of heat from the charging process. Yeah, the compensator just lives in the charging line. Yeah, two types of thermal compensator: one for connection to the oxygen cylinders. The other for connection to the shut-off valves of the regulators. Those fitted to the oxygen cylinders have a special nut fitting that attaches directly to a cylinder, and downstream the end is a flareless coupling. Don't need to worry about that. Just need to know that the thermal compensator is there to act as a heat sink to prevent any buildup of heat during the charging process. Yeah. That is written down on page 47, about halfway down. The compensators act as a heat sink to disperse any buildup of heat. That is what we need to know from here. The other thing with oxygen, before we connect the oxygen trolley to the aircraft, take the hose, take the blank off the hose, and run a bit of oxygen through. So if there's any crap in the line, it's going to get blown out. It's not going to get introduced into the aircraft. At the same time, while you're gently blowing the hose out, have a sniff of the oxygen. If that oxygen's contaminated, it's going to smell like rotten eggs. It really hums. It's horrible. Yeah, and you don't want to be putting contaminated oxygen into an aircraft. So when you're purging the hose from the oxygen trolley, before you connect it up, just have a wee sniff, just to make sure that you're not introducing, as I say, contaminated oxygen. And I think that's pretty much it. Thermal compensator. There are revision questions at the back of the notes, and those revision questions pretty much cover everything that you need to know. Use those for you to help you as you're going through. I'll have a look. I'll see if I've got any additional questions that I can send off to help you out. But the ones in the back of the book are pretty good. Yeah, they cover all the relevant points that we've made today. That takes us nicely to the end of the oxygen subject. Has anybody got any questions, queries, anything at all on anything that we have covered today? No? So everybody's happy with what we've done today? No problems?
Yes. Hello, Jim.
Yeah.
Hello. Can
Hello.
you explain this typical continuous flow oxygen system from chapter 1 again?
From chapter 1?
Yes.
Just let me see where we are.
Yes.
That one. Right. Your oxygen
Yes.
cylinder, yeah? It's an unpressurized aircraft, so it's what they call continuous flow. When I turn the system on via the control knob, oxygen is just going to flow to the masks. Yeah, that's all it is. And if we're going to fly above 10,000 feet, yeah, the pilots and the passengers are going to plug their masks in at the relevant location, yeah, and breathe. Yeah, and that's all it is. As long as that system's switched on, yeah, that oxygen is just going to carry on flowing till it runs out.
Okay.
Yeah?
Okay.
You sure?
Sure, Jim.
Anybody else got any
Mr. Jim.
questions?
Mr. Jim.
Yeah.
I have asked you about the color code red, orange, and green. And on what the red, orange, and green color code are found? On the cylinder or in the where? On the max cable or
on
where we
the
get
mask connections.
mass connections?
Yeah.
You said that you will show the figures.
Yeah, where the supply line is, yeah, where we connect the mask in, depending on what the aircraft's doing, we can change these connectors. And these little orifices just go into the mask connectors, and they are just regulating the amount of oxygen that we're allowing through to the mask.
Okay. In the max, we can get red, orange, or green. Different types of masks are there, yeah?
Not the masks,
Then we have
but the connectors for the masks, yeah, and they'll be color coded. Depends on the way it's fitted. Some of them might just have a bit of tape around them. Others might be the whole body might be coloured red or orange or green or whatever it might be.
Okay, thank you.
Yeah. Now, don't forget these are on small unpressurized aeroplanes, so you're not looking at a huge job to change these things. Yeah, depending on what you're doing with your aeroplane.
Jim.
Yeah.
That there's one point. This advantage of chemical oxygen generator.
Yeah.
If an emergency descent has taken place and the generator have been used, they are simply replaced.
They're what?
Why during descent? Why?
Because you'll have had a depressurization. Yeah. I'm just trying to find the relevant page.
Page number 29.
Yeah. The oxygen that's coming from the cylinder, when we initially fire the cylinder, yeah, it's producing quite a lot of oxygen, and then as the chemical reaction carries on, the production, the rate of production of that oxygen slows down. Yeah. So if you're flying along quite happily, and let's say you have a depressurization, the masks are going to drop down. You're going to pull the lanyard, put the mask on. Yeah, that high flow rate of oxygen, yeah, is going to keep you going while the aircraft comes down in the first part of an emergency descent. If you think normally the aircraft's going to be flying 40,000 feet, yeah. If we didn't put the mask on and provide plenty of oxygen for each passenger, then they're going to be physically disabled. Yeah. So as the aircraft comes down, as it's reducing in altitude, the air's becoming thicker, more oxygen becomes available. Yeah. So the high flow rate just compensates for that lock of oxygen at the higher altitudes. As the aircraft's descending, as the chemical generation slows down a bit, yeah, we're not so badly off. So initially, yeah, we've got that high flow rate, and that helps us as the aircraft's coming down through the first part of its descent.